Welcome to the third day of Hot Interconnect. Today is our hands-on day, and we will have two tutorials that are provided by Ohio State University. And our session chair, Mike, will introduce our tutorial presenters. Welcome once again, and have fun.
Hello everyone, welcome to our tutorial. We have DK Panda and Nawras Alnaasan for our tutorial this morning. DK Panda is a professor and university distinguished scholar of computer science and engineering at Ohio State University. He serves as the director of the newly established $20 million NSF Institute, Icicle AI. He has published over 500 papers in the area of high-end computing and networking, putting voltage high performance MPI over InfiniBand, OmniPath, high warp Horsey and Slingshot libraries designed and developed by his research group are currently being used by more than 3,450 organizations worldwide in 92 countries. More than 1.91 million downloads of this software have taken place from the project's website. This software is empowering several InfiniBand clusters, including the 21st, 67th, and 88th ranked ones in the top 500 list. High performance and scalable solutions for AI framework from his group are available from his website. Similarly, scalable and high performance solutions for big data and data science frameworks are available from his website. Professor Panda is a fellow of the ACM and IEEE. He is a recipient of the 2022 IEEE Charles Babbage Award and the 2024 IEEE TCPP Outstanding Service and Contributions Award. More details about Professor Panda are available at his website, which you can find on the hoteye.org website. Our next presenter is Nawras Alnaasan. He is a graduate research associate at the Network-Based Computing Laboratory in Columbus, Ohio. He is currently pursuing a PhD degree in computer science and engineering at Ohio State University. His research interests lie at the intersection of deep learning and high performance computing. He works on advanced parallelization techniques to accelerate the training of deep neural networks and exploiting underutilized HPC resources, covering a wide range of deep learning applications, including supervised, semi-supervised learning, and hyperparameter optimization. He is actively involved in several research projects, including the High Performance Deep Learning Project and ISCO, the Intelligent Cyber Infrastructure with Computational Learning in the Environment. Alnaasan received his BS degree in computer science and engineering from the Ohio State University. Thank you all for presenting.
Thank you, Mike. It's a great. Thanks for the introduction, and Aten, thanks also for the introduction. So I think we can proceed. Let me share the slides just to make sure. Can you see my slides?
Yes, we can see them,
Okay.
Dr. Panda.
Yeah, in the presentation mode and all. Okay.
Yes.
Okay, so good morning again, everybody attending this tutorial. It's a great pleasure for me and Nawras to go over this tutorial, which is titled Principles and Practice of Scalable and Distributed Deep Neural Network Training and Inference. And it's a half-day tutorial. We'll be trying to take a break or around like a 20 minutes break, might be around 10, 10, 10, 10 Pacific, depending on how we progress here. And the slides are available. Either you can go here directly, go.osu.edu, hot I-25-IDL. A link also has been posted on the Slack. So please feel free to ask your questions on the Slack, and we'll be very happy to answer. So the tutorial will be covering this, the outline. As you know, this field is very hot. A lot of things are happening. We want to bring you a very comprehensive view of what is happening in this field, both in the distributed deep neural network training as well as in inference. So we'll start with a very high-level introduction. If you are totally new to this field, or you would like to know a little bit about the past, present, and future of AI, we'll start that. We'll introduce machine learning and deep neural networks, and we'll just give you an overview of some examples of applications of deep learning so that you will get a feel for it. And then gradually, this is like a very like a 100,000 feet view, and gradually we'll go down. So then we'll introduce the different kinds of deep learning frameworks, what we mean by deep neural network training, and especially since you know this is the hot interconnect, we are always looking for scale up, scale out issues. So we'll be focusing a lot of principles on distributed data parallel training to start with. And we also have a hands-on exercises we have reserved. We have in that the issue. We have a GPU cluster, and we'll actually provide you accounts and all. We'll go there in a little bit later, and then you can actually run some of these things. So we have set it up so that you can actually get a feel how the data parallel training runs. And then what we'll try to do, we'll take a quick look at the latest trends in what is happening in the high performance computing architecture, that is like a CPU, GPU interconnect, and then try to bring some bigger challenges, like how do we really take advantage of, let's say, 1 million GPUs people are talking now to carry out distributed training. And in that context, we'll go into the advanced distributed training. Okay, so data parallel training is common. A lot of people use, but once you go into very large scale large number of GPU, we are also hitting into billion parameters model. Even people are talking about trillion parameter models. So you need to come up with a very advanced parallelism, like a model parallelism, hybrid parallelism, spatial parallelism, tensor parallelism. A lot of new parallelism concepts are coming. So we'll be introducing those. And also we'll be taking one such example of this advanced parallelism, and we'll try to do the hands-on. And mostly will be, as you can see here, we'll focus on training, but this field is not complete if we don't understand inferencing, because that is also getting very important these days. So we'll actually go over some of the distributed inference solutions, and then we'll try to close with open issues and challenges, and then conclude. Now, this is the morning tutorial we're giving. We also have a tutorial, myself and another student, Ben, will be going into the high performance networking technologies, latest starters and trends. So that is in the afternoon. So here we'll assume that you will be knowing reasonable idea of the HPC systems, but in the afternoon tutorial, we'll really go into more details on the networking challenges and issues. Okay, so that's how both these tutorials have been designed. So if you take a very broad look, the field of AI, we just want to keep some terminologies well defined. Whenever people are talking about machine learning, deep learning, AI, some people get confused a little bit. So this is how the field looks like. This is the big field of AI. And this AI field has been there for many years. We'll talk about that in the next slide. And then over the years, people have been focusing a lot on machine learning, which is a subset of AI. Okay. So the machine learning, if you see this picture here, if you have a set of inputs, you basically want to do some feature extraction and try to do some classification and then come up with a model, like a machine learning model. And then if some new input comes, you use that model and get the output. So this also has been there for many years, as you can see, like since 1980s. But then this machine learning field, a subset field got created, which is deep learning. And as you can see, the problem remains the same, but the approach is a little bit different. Instead of having kind of a feature extraction but by a person or a human being involved, the challenge is like how we can combine these two steps and totally give it to a system. Okay, so that the human is not involved there. Can the machine itself learn? And that is the field of the deep learning. Okay, and that's what we will be focusing on, focusing quite a lot today. Now, if you take a look at the slide, it's in fact, if you go back, people were thinking about even not exactly AI terminology was not introduced, but people were thinking about this learning even starting from 1805. If you go back in the field of mathematics, like linear regression, PCA, all these concepts started in 1800s. And these are all the heroes of the field who have actually contributed to the fields. These are the giants, and we are standing on top of them or their contributions to really make progress. Now, of course, here you will see, I mean, people, of course, the Turing machine was in the 1936. People talked about electronic brain, perceptron, Adeline. So this was a kind of a golden age. A lot of things happened in the field of the intelligence in general. Even if you go back, you see the K-means, which is a very common algorithm, which is being used these days, was invented in 1965. But then, as this neural network and all these concepts came, there were a lot of ideas, but then people were not able to validate those. And that's what is called like a dark age or AI winter, because people had ideas, but people are not able to validate because appropriate environment was not there. And when I mean by environment, computing infrastructure was not there, data sharing was not there. And that's why things got slowed down. But then in the recent years, that's what exactly has changed. Okay. And that's where we are seeing that the growth is going on. Not only like newer concepts are coming up, newer models are coming up, but now we have actually very sophisticated large scale CPU clusters, GPU clusters, high performance networking technologies to put together these clusters to really run these things and validate. And also we have huge amount of data sets. So this is where, if you broadly take a look, we'll go into a little bit details on the later section, but starting from like this 2014, if you go back almost like 11 years back, this ImageNet challenge started. Okay. And at that time, it was very early, but that was also the early stage of the GPUs. So almost the 90% of the teams use the GPUs. Then, of course, over the years, Kaggle community is also continuing these challenges. So these kind of issues or like the schemes are helping the community to actually continue to make progress. If you see like I believe most of you are familiar with this top500.org. So this is like the top 500 list in the field of supercomputing, which gets announced twice a year, once in June in Germany, once in November in US. And if you take a look at like it's a distribution, just the latest one, which was published 2 months back, 215 out of 500 systems are actually using accelerator or co-processor, and here it shows some like a breakup across different vendors and all. As you know, the NVIDIA has been continuously pushing on this dedicated kind of a DL supercomputers, even NVIDIA example of AI supercomputers. And also we see like on the El Capitan, which is like a number one top 500 hosted system, is using AMD. So it's a combination of all these systems, AMD, NVIDIA, CPU, GPU, when Intel GPUs are there on the Aurora system. So they are actually allowing people to train this kind of larger scale model. That is like in a more like a research area. And as you know, even a lot of companies, Microsoft, Google, OpenAI, Facebook, they are also very actively working in this area. So this is what like over the last several years, if you take like last 10 years, this is what actually people projected, like AI revenue will continue to grow. And that's what is exactly happening. Okay, the continuously growth is taking place. But if you take a look at like this is just a sample. Now, of course, every field is embracing AI. But this was a study which was done in under this the market saying that in the 2025 it will hit $36 billion market. So this was kind of the different domains where people expected AI will be happening in a very significant manner, and that's what is happening, like a contract analysis, object detection, object identification, geophysical feature detection, text query of images, content distribution in social media, predictive maintenance, patient data. The entire field of medicine is totally hungry for AI-based solutions, static image recognition, classification, and of course, the field which is also embracing AI is the stock market, like the algorithm, the trading strategy, um, uh, to make sure that the Wall Street actually makes a lot of money. So that's how the field is evolving. So if you take a very simple look at it, now let's look at the principles, trying to define some of the terminology properly. If you take a look at the very traditional machine learning, we talked about like the field of AI, then we have the machine learning, then we have the deep learning. So in the machine learning, there are basically these three kinds of machine learning. One is a supervised learning, and this is very similar to the picture I showed on the initial slide. So if you have some data, so then typically you go through some kind of an algorithm, and you're trying to do this processing, and there is a human in the loop. So the person is actually looking at the data, looking at the model, and trying to correct it, and then coming up with this model. And then the next time the data comes, we are able to exactly categorize them into different classifications. Unsupervised learning is an advanced version of that. So where the human person is not involved, we are giving a similar kind of approach to do the interpretation and do the processing and come up with the model. And recently, there is an advanced version there also available, which is called reinforcement learning. That means based on the model and based on the data, you can see there is a loop here. So that means this model is continuously being improved based on the newer kind of data, newer kinds of decisions. So it is like it is trying to learn itself. So that is the very traditional machine learning. But then, as I indicated, a subset of the machine learning field is the deep learning, and the common thing what you see is called a deep neural network. I'm sure many of you would have seen these kind of diagrams in any paper in the deep learning. So this is called like an example of 3-layer deep neural network. Okay, there is an input layer, there is a hidden layer 1, hidden layer 2, and an output layer. So it consists of a set of like a nodes and the set of edges, and then this is what we are trying to do the training on. So in fact, if you take a look at it, what is this kind of deep learning is trying to capture exactly what happens in our brain. Okay, if you take a look at like this left hand figure, I'm sure if you would have taken in your middle school or high school biology class, you would have seen a figure like this. Okay, and that what it means that okay, we have a cell body, there is a nucleus, and there are these dendrites, and then you get response or the impulses, and these impulses are get processed, and then over the action, these impulses are carried away from a cell body to to the other branches of the action. So our brain consists of billions of these biological neurons, and that's what exactly we are trying to mimic in our deep learning framework. And if you take a look at the right hand side, is actually the equivalent of mathematical model. Okay, so what we are trying to do, this is like a nucleus. So this is a cell body. We have all these edges, as I showed earlier. So this is like a node. These are the edges. There are different weights, and then based on some kind of an input, it is trying to actually perform this kind of activation function, and then puts it into an output action, which is getting connected to the to the next one. So this is just only one, but what we want to build, when we say like a billion parameter model, now people are talking about trillion parameter models. So this is like you can see huge number of these nodes we are trying to connect. So then the question is, in this deep learning, of course, there are like two phases. One is the training. And this training is very similar. So let's think of like we as human beings, how we have been trained. If you think of like a child is born, just to give an example, let's say fire. The child doesn't understand what the fire is. Okay, the baby, as they are growing up, you will see like they will put the finger in the fire. Okay, the first time they will get a shock, might be second time, third time. So then the neurons are getting connected, saying, yeah, fire in this shape, in this form should not be touched. Okay? Same thing happens with driving, like or a swimming. If you try to go the driving, there are some certain rules. In the beginning, you make some mistakes, and from those mistakes, you try to learn, and then over a period of time, you try to be a good driver. Okay, and this is exactly the same that in the beginning when we are trying to come up with the training. So think of like this is the deep neural network, and we have a huge set of data, and then here we are like this example is trying to show, can we detect a human face? Okay, so based on this data, we are adjusting this model, we are training, changing all those parameters to make sure that the final model is able to actually identify the human face correctly. Okay, so now of course, let's say in this case, like the training data, like so if you put some dog's face in the training, the model should be able to generate some error saying, oh, this is not the human face. Okay, and then but we learn through that process, and once this model is done, once the training is done, the next phase is actually the inference. Okay, so here we go over multiple passes for the data, but the inference is actually a new human person is coming, or you take an image and you are trying to say, okay, whether this is a human face or not. So that is the kind of the inference we are talking. And with respect to the complexity, training is the most compute intensive. Okay, that's what we'll go into, and we'll understand the principles and the practice. The same thing is happening in inference. It's a single pass for data. It should take some seconds. There is no model adjustments, but inference happens in bulk. Okay, so think of like a drone flying over a field. Let's say in the field of digital agriculture, it is trying to understand, okay, what kind of disease has happened to the field. So you need to see continuously. You have the newer and images, and you are trying to detect or make some decision out of it. So this is where like you need to make sure that you not only have low latency inference, but also high throughput. Okay, and of course the bigger example these days is the chat GPT and all the LLMs. We'll talk about that in the next few slides. And since this training over huge amount of data, when you have billion parameter or trillion parameter, even it's like thousands of GPUs, even hundreds, or even people are talking about 1 million GPUs. So this is where the parallel distributed training is very significant, because you cannot just do that with one GPU. So to understand these concepts a little bit better, um, there is a very nice demo here. We'll try to show you, which is called TensorFlow Playground. Not sure how many of you have seen. I'll stop the sharing, and Nawras will play that, and then we'll get exposed to a lot of these concepts. Okay, so Nawras, I'm stopping.
Okay.
Please share.
Can you see my screen?
Yes, yes.
Okay, perfect.
Why don't you go over? Yeah,
Okay,
Nawras,
sure,
just yeah.
sure. So this is just to give a visual representation of the training process. Okay, so we'll cover these things in more details later on, all the different terminologies. But assume that you have this data, right? Data points on a two-dimensional plane. We have these orange dots and then the blue dots, and the goal of this training is to basically be able to classify the different classes, right? So classify if it's an orange one or a blue one based on this training data, right? And this is the neural architecture. So we have two input features, and then the two input features are just basically the X and Y coordinates, and then the number of neurons that we want to train in the network. All of these connections are the weights or parameters of the network. So let's try and train this network. And you can see after multiple epochs, so epochs uh, means one pass over the entire data set. After multiple epochs, we see that the network now converges to a solution, right? So we have a decision boundary in here. And then anything that falls outside this decision boundary is classified as orange. Anything inside is classified as blue. And as you can see, there are so many different hyperparameters that we can play with, like the learning rate, meaning how fast does the network learn from the training data. We have the activation functions. We'll cover that in more details later on. Um, we also have like different data distributions, right? So some of them are more complex than the other ones. Um, and as you can see, some of them are linearly separable, meaning you can draw a single line to separate them. Some other data sets are more complicated, right? So, for example, this data set is linearly basically unseparable, right? Or so you need more complicated network to be able to capture this complexity. So this is for the training part. We can move to the inference part. So once we have a trained network, now we can use that network, deploy it, and use it for inference. So for example, here we're using the ResNet 50 model, a vision model trained on the ImageNet dataset. And as you can see, we can like upload an image or just give it an image from this list. Let's say we give it a image of a dog. You see the inference time here, and then these are the different classes that the network predicts that this data sample belongs to. So you see it has different confidence rates in different classes. Maybe let's try another image here. Bridge. Okay, so as you can see, like depending on the image, the confidence can be different, right? So it's detecting 54% harp, 44% suspension bridge. So depending on the training data, right, if the network have seen similar samples in the past, it will be more confident in its prediction. And this inference is run on the GPU. Let's try it on the CPU. So let's pick the same image here. So it took almost more than half a second compared to only 100 or 200 milliseconds on the GPU. So CPUs can still perform inference, especially if you have many CPUs. You can do it quickly, but the GPU is the better architecture because of the matrix multiplication that's happening underneath. It can take advantage of the GPU architecture.
So, Norris, there is a question on the Slack
Yep.
from Bob Lance. For this current example, are the test data a subset of the training data or are they independent?
So for this example, this is trained on ImageNet. So ImageNet is a general data set, right? So it has more than 10,000 classes. Um, and it tries to capture everything that is common, right? But you can also upload your own images. So if you upload your own image, then you know that it does not exist in the training data set. This particular image, I'm not sure if it's in the ImageNet data set or not. Could be not. Um, but I mean, feel free to visit this link, upload your own image, and see how it performs.
Okay. So, Bob, I hope this answers your questions. Again, to all the attendees, if you have any questions, please feel free to post it onto the Slack. Nawras and I will be monitoring, and then we'll be happy to answer back. Okay. So let's then continue. So hopefully these two demos actually provided an example of like a concrete scenarios for training and concrete scenario for inferencing. So now we'll continue. Let's take some look at real life examples of AI. So we'll start with like a machine learning. So here you will see like a very simple example, but it's a very large market is credit card fraud detection. Many of you would have seen like over the years, this credit card fraud detection issue is continuously there, but better and better solutions have been are getting designed. If you go back like a 10, 20 years back, I'm just giving you an example. If you used to go in an international travel, there was an expectation that you tell your bank that you are going on a foreign trip, so that if you do some purchases there, it is treated as a valid purchase. Okay, but over the years we don't have to do those kind of things. The reason being, now not only like a, let's say before I went for an international trip, I also purchased my airfare using my credit card. So my bank actually knows that I am heading into that direction on certain and certain date. So using this kind of data, they are bringing or generating these models. And these are the kind of the machine model. And here if you see like a, based on the model, based on the current data or based on the current pattern, the model is able to say, okay, what is the percentage of probability of fraud? Okay, and then there is some human being is involved, which is trying to understand that correctly or not. Okay? For example, I might be going from Columbus, Ohio to let's say Germany, but while I'm in Germany, let's say I'm making a registration for a conference in Australia. Okay, so so then the model might be able to might generate an error. Sometimes also I've seen it says that okay, this purchase you are trying to do from Germany while being in Germany, but your credit card number is being used in Australia. So that means this may need some additional processing. So like this kind of a fraud detection, as it says, like in 2019, almost 112 million was lost. Okay, and so all these banks are trying to continuously build better and better machine learning models to solve this problem. Here there are some examples. These are like a deep learning examples, like the traditional high performance computing. Let's say think of Boeing, think of Airbus. Continuously they used to do a lot of large scale simulations, but then over the years, what they have found out, like if you do very exhaustive simulation, all combination of like all possible parameters combinations may not lead you to the best results. Can we detect that? And if so, we can really accelerate our simulation. And that's what a lot of these days called AI driven simulation, HPC simulation. That's what they are trying to do. Here, there's another example of like think of like a not in the traditional engineering, but like a painting. So let's say there is a doodle here. And if I give this doodle, can actually the machine try to draw it as if Picasso would have drawn? Okay. So it's a very complex thing. I mean, so that means a machine has to really understand what is the stroke Picasso does, and then given a doodle, it actually tries to convert that. Okay. So I'm just giving a few motivational examples. So here again, very simple is like hey, I go to on foreign countries. If I want to buy something for my daughter, I'm trying to understand like what is written there. I don't know the exact language, but then Google Translator can be used. Same thing here. If you land in a foreign city, you can use your Google Translator automatically, and it shows you where the exits and all. Of course, self-driving cars. We hear a lot about Teslas and all those things every day news, and that is kind of the panacea. People are trying to use the AI-based driving for not only for our regular driving, but the automated trucks, even planes. Everywhere there is a focus. Here is a very nice example. In fact, from the Ohio State University campus, if you go, these are the actually there's a small delivery vehicles You can think of like a small robots kind of thing, but these are like the miniature version of Tesla. You can think of if you want to order a coffee or a lunch, you just put it on your iPhone, and the cafes which are in the campus, they actually load those things to one of these small vehicles, and it actually comes to your building, and then it sends a message, and then you come down with a code, and then you open it up and take it. So they have totally mapped the entire campus. And these actually vehicles, as you can see, go on the sidewalk. They stop when the automatically detects there is some people are crossing, the cars are crossing, and this is the field you will see is gradually expanding. Okay, so this will have significant impact in distribution of groceries, food, packages, mails. Continuously, you might be hearing that this is what is happening in many different countries, cities across the world. Of course, the medicine field, as I said, is very hungry for AI. I mean, think of like a very simple example of like a everyday, if we like a, let's say we fall sick, we go to our hospital, and the doctor says, okay, do a blood test or an urine test. And of course, there's a pathologist involved. The pathologist actually looks at the data and then gives the summary. It still takes some time. But then if you see with respect to common diseases in any hospital, thousands of such tests get done. Okay, and many people might have a very similar kind of uh, uh, diagnosis. So the question is like, can we convert that into an AI framework? In fact, OSU, within OSU and many other universities, there are a lot of work taking place here. So the question is, we are not giving the final decision to the machine, but it automatically is trying to, it can be trained over all this data. And when a new data or like a patient like me goes and my blood test is compared, or that we do an inference on my uh, blood test data across the trained data, it can narrow down and it can say that, yeah, I might be having a flu, or I might be having this kind of things. And then the pathologist, instead of spending like a 10 minutes, now can decide in 2 minutes. Okay. So that helps a lot significantly to reduce the kind of the cost, the healthcare cost, which is rapidly rising, especially in the US. So now those are like we got exposed to basic training and inference, but all of you must have heard of the Gen AI. Okay, so that is the generative AI. So generative AI, as again it says, like it's a subset of that deep learning, which creates new content like text, image, videos, or audio based on the data it was trained on. Okay, and that's what also happens. Like in this case, like of course, a lot of these examples are there: text, image, videos, or audios, and and this also we can relate to our human beings. So you remember I gave an example of driving. Okay. So let's say you learned your driving in your home city, let's say in Columbus, I learned the driving, but then tomorrow I'm going to Chicago or Los Angeles. The question is, can I still drive there? All right. Because I was never trained there. Okay. But I should be able to drive there. So these are kind of the new situation, and it's trying to create based on what it was trained on. And same thing like a student, like all of us have taken classes and all, in the courses you will get taught, but then you have an exam, and the exam, the questions are not exactly what you were taught on, but you were taught on some concepts. Now the question is, are you able to answer those questions which were not being trained? So that is kind of a Gen AI. And then the Gen AI inference. So this is what I think is making a big impact here. As you can see, this is the large language models. So there what happens, like you ask a question, these are the kind of the prompt engineering. And here you see like the model generates output based on input components. And especially for the autoregressive models like LLMs, inference follows an iterative loop. Okay, and we'll talk about this in the second half of the tutorial, like this generates a token and they are fed back as input for the next step until completion. Like if I ask a question and then we divide it into smaller pieces, and then we're trying to get the answer and put them together and give a response to the user. So here there is a lot of these concepts we need, because we need low latency, you get very fast response, efficient batch processing. Because if you ask like a chat GPT, your request is actually being executed on some server. So that server is actually getting millions of such requests. So how do you actually do processing on that server. This is where like people are talking about even the mixed precision support. We'll talk about this, and especially when it is running on the backend server, it consists of a bunch of CPUs, GPU interconnect, and that makes a big impact. Also, the memory bandwidth also makes a big impact because the data is stored on your GPU memory or in the CPU memory, and you need to do inference. So we'll be touching all these things in a much more greater detail later on, but here we are just introducing the concepts. Any questions so far? Please feel free to post it onto the Slack. And Nawras, I believe you're monitoring. If there is any question, please interrupt me. So with that kind of a background, now let's try to to understand what do we mean by deep learning frameworks. Okay. So if we go back in the history, this is what, if you take a look several years back, this Google actually started this project called Artificial Brain to learn to find cat videos. Like, as you know, in the internet was full of a lot of things. They took a very simple objective, saying if you give hundreds of thousands of videos, can you actually identify that, oh, this corresponds to a cat video? Okay, so think of it as like a classification of videos, automatic classification of videos. That's how the project started, and they were able to succeed. And in that case, of course, as you can see, like they used Google's 16,000 CPU systems to identify a cat. So then that internally they had updates to their models, and also that these are some of the news items in the history. They were able to successfully say that, oh, now this deep learning can actually work. So similarly, then gradually they saw. I mean, this is where the complexity came. I mean, they were not able to do it like a one computer or two computer, but they had to use like a 16,000 computers. So that's what was the kind of the neural network with 16,000 computer processor with 1 billion connections. So their model had 1 billion connection, and this network actually browsed the YouTube and began to look for cats. The data sets were like they were randomly selected on the YouTube video thumbnails. There were 20,000 different items. And then whatever that model, they were talking about that, saying this is a Google brain. It achieved 81.7% accuracy in detecting human faces, 7% accuracy in identifying human parts, 74.8% accuracy for cats. And actually, at that time, they used these concepts of model parallelism. It was not very open at that time, but that's what they used. And this is, you can think of like in a very early phase of this field. And then gradually it moved. This concept, as it started picking up, it actually, this paper, if you see, it was published in ICML 13, almost like 12 years back. So they solved a similar problem as identifying cats, but then they started using GPUs. Okay, a large number of GPUs being connected, but then the bigger challenge was how you do the GPU to GPU communication. And this is where actually, if you take a look at this paper, this was the standard COTS, like the commodity technology systems you're trying to do, commodity supercomputers you are trying to use. And in our group, some of you know, we have been, for the last 25 years, we have been working on a high performance MPI library called MBAPICH. They actually used our library. That was the first time they are trying to use the scale out using MPI library to get this running much more faster. Okay, at that time, a lot of these like collective libraries like Nickel, RICL, and all those things didn't exist. Very simple MPI was there. And in fact, we'll take a look at this much more later on. And in fact, these days we have solution, or continuously we are working on solution. And in fact, we'll try to use that also in our hands-on exercises, because the MPI, which is a message passing library, actually performs very well point-to-point collective operation. You can actually carry out all these deep learning training, inferencing without needing Nickel or RICL or any of those collective communication library, because MPI for last 30 years has been supporting these collective operations, and the field of AI is now discovering that. Okay, so we'll actually take a look at that. This is where in our group we have been doing a lot of vendor neutral work, so that you can purely use MPI library and then trying to get, in fact, equal or even better performance, okay, of training and inferencing. We'll talk about that later on. So then, as what happened, like as the GPU technology evolved. So this is where NVIDIA started the CUDNN library. It's basically a GPU accelerated libraries for DNNs, and it actually provides the forward backward convolution, pooling, normalization, activation, and that has actually led to all these what you call like a frameworks. Okay, like it started with Cafe 2, Chener, the Microsoft Cognitive Toolkit, MXNet, Paddle, TensorFlow, PyTorch, Torch. So like this over the years, a lot of these frameworks have evolved. Now the question is why these frameworks? Okay, so you remember I talked about all those brains, neurons being connected. You can actually, if you are a, you can actually even do the training using those kind of concepts. But those you can think of like a assembly level program. And as you know, just like on our regular systems, assembly level programming is very hard. So that's why we want to abstract it up. And this is where these DL frameworks try to abstract it up, and they hide complex mathematics, allows users to actually focus on the DL models. It provides support for different parallelism. And here it exactly sees like a data flow, things get done. And of course, the architecture is also evolving. You must be hearing like a tensor cores and all. The traditional CPUs, GPUs used to do floating point operation, which was traditionally for high performance computing or integer operation. But now they have been converted to do all these matrix vector, matrix operation, which are core of the deep neural network training. And this is where we see a lot of actions taking place. Okay. So that has led to this over the years. As you can see, these are like some of the important one. The Cafe, TensorFlow, PyTorch, CNTK, etc. has come. Some of them have been dying also, and newer ones are coming up. And of course, at some time there is also this focus saying that okay, let's say I have trained using TensorFlow, but now I have a new set of data and I want to retrain. Can I still use TensorFlow or can I move to PyTorch? So like this, there is also a new open neural network exchange or called Onyx format has come. Now, especially these days, if you see, we have some data in the next few slides. The PyTorch is actually getting a lot of traction. Okay, TensorFlow is also there, but the other frameworks are there, but the most leading one is the PyTorch. It started actually, as you can see, PyTorch is a Python adaptation of Torch. Written was Lua. It was released in 2016. It has gained a lot of traction. And it started as like several contributors and mainly backed by Meta. And there is a kind of an approach. They use something called a define by run. That means as you are going and getting training, you should be able to modify the model and all. So that was not there earlier. Okay. So it was more like a static. A lot of features were added to make it much more dynamic. And then that has, of course, support that has support for GPU acceleration, integration with NumPy, and that is getting a lot of traction. Of course, if you there are a lot of other alternatives here also. We're just adding these as a pointers. Might be you have used some of these, or if you want to use, in fact, here, for example, Lawrence Livermore National Lab, they had a framework called LBAN, and that was geared towards more scientific deep learning with a scientific data set. Okay. Similarly, here there is a deep scalable sparse tensor network engine. So you will continue to see people may come up with better and better of these frameworks also as we progress. And here taken ideas just like let's say the open source frameworks you are talking. This just gives a perspective, and it's an AI index report, and it provides a lot of different stats. So especially if you take a look at this link, it reported in 2019 saying that okay, PyTorch is winning over TensorFlow. Okay, so prior to that it was TensorFlow, but since 2019, last 5-6 years, PyTorch is taking over. And as these models are also coming, the question is how do people access the models? And this is where some of you must have heard of Hugging Face is now the largest model repository for the trained and tuned state-of-the-art models. So different community, different people have the models, and then they contribute back to Hugging Face, and then you can actually take and then use it from the Hugging Face. So since that is the largest repository, so here, if you take a look at some stats, like a number of top 30 models on the Hugging Face, so you will see that the PyTorch and TensorFlow is taking a lot of importance, and especially if you go into more downs, like the PyTorch only is much more significant compared to TensorFlow only, or this is the right hand side is across all the models. The left hand side is only top 30 models. And that's what it says, like a 92% of the models are PyTorch exclusive. And it is not just the models which are being contributed. Of course, a lot of publications are coming, research papers, papers with code. And here also we see the very similar trend. Like you see, this is the TensorFlow, this is the PyTorch, and the PyTorch here is continuously growing over the years. And here it says like a statistics like 7% in 2017 to almost 80% in 2021. And here also the statistics, this is the latest quarter, like when it was released in 2023. There has not been any updates since that time. So it was almost more than like 70% was like a PyTorch repositories. So I hope that gives you a very broad perspective. Like these are like 100,000 feet level, getting exposed to terminologies, getting exposed to the field, what is happening. But now we'll try to start diving deeper. Okay, and so then we'll go into a little bit of the basic principles of how a training takes place, deep neural network training, and then Nawras will cover this part. But if you have any questions, please feel free to post on the Slack, and as we go, we'll try to cover those things. Nawras, are there any questions on?
Let me check the Slack channel quickly. I do not see any questions at this point.
Okay. So then let me stop here, and you can share and then continue.
Okay. Okay, you can see my screen, right?
Yes.
Okay, perfect. So yeah, next section will be on deep neural network training. So before diving into the exciting part, right, the distributed training part of this tutorial, we need to cover some background. Some of you might be already familiar with this background, but it's basically just to give baseline understanding of the sort of calculation or computation that is happening when we train a DNN. So okay, let me see if I can move this. Okay, perfect. So this is a very simple DNN, 3 layers, right? So we have an input layer, 2 hidden layers, and an output layer. We call it 3-layer network because we don't count the input. This is the convention. And the training involves 2 main phases, the forward pass and the backward pass. And simply the DNN is just a mathematical function, can be a very complicated one, but it's just a mathematical function that takes input and then it gives output. And then the weights or connections between the neurons of the network, right? So every white circle here is a neuron. These weights are just coefficients, right, of the different parameters in that mathematical function, right? So the main purpose is that when the network sees a data sample, it gives a prediction, right? So it does the forward propagation. Forward propagation is simply multiplication. So take the input x multiplied by W1 and W2 to get the values of the neurons in the next layer, and so on. You continue this propagation until you get a prediction or output, right? So this prediction is compared to a ground truth value, the correct answer, to calculate the error or the loss of the network. So this will tell us how far are we from the correct answer. Based on that, we're gonna do the backward propagation, the backward pass. And as you can see, these values, E7, E8, these are called the gradients. The gradients will tell us in which direction should we change the weights or parameters of the model so that in the future, if we see a similar sample, we give a more accurate prediction, right? So the gradients just tell us the direction of change that we should apply to our network. Yeah, and once we complete the backward propagation, that's when we apply the weight update. So backpropagation involves complicated math. Luckily, in DL frameworks, you don't need to worry about the math. You just go model.backward, and all of this gradient calculation will be done for you. But just to get an idea, this is just a even simpler example where we have an input x. Theta 1 here is just the weight for the first layer of the model, and then we have an activation function. We're going to talk about this in a little bit. So this is how the equation looks like. We have this activation function g, and within that function, we have simple multiplication, theta 1 by x, the input. And we take this output and we use it now in the second activation, right? So this is just the forward propagation. Now, during the backward propagation, we need to calculate the gradients. So take that derivation of this function, and by doing that, we'll just find the rate of change that we need to apply, the direction and rate of change. So what are activation functions? ReLU is a very common example of activation functions, and the purpose of it is just to introduce nonlinearity, right? So we talked in a couple of the previous slides that some of the data is linearly separable, right? So you can draw a single line to separate the data set, and that would be your decision boundary. But now, what if your data is more complicated? We need to introduce a more expressive function to model this data. And this is basically the purpose of the activation function. We have so many different flavors of these. Sigmoid is one of them. Hyperbolic tangent, ReLU, and leaky ReLU. And as you can see, these functions will just take the output of the multiplication, right, the weights with the input, and map it to this distribution. So if it's in the sigmoid case, if it's negative, the input, then it will be mapped to a value between 0 and 0.5. If it's positive, it's going to be mapped between 0.5 and 1. And as I said, ReLU is the most popular activation function. You'll find it used in most of the neural networks nowadays. Now, one very important concept to keep in mind is the learning rate. So we said that the gradients will tell us the direction. Now, the learning rate will tell us the magnitude of the change that we're going to apply to the model weights. And the learning rate, it's a hyperparameter, so it's defined by the user. So the user will choose the learning rate in order for the network to learn as quickly as possible and converge to a very good solution. So if you look at this figure here, j of theta is the error function. So lower is better. We want to minimize the error as much as possible. Theta is just the parameters, the value of the parameters. If we pick the learning rate to be too low, we need so many training steps, right? So many forward passes, backward passes in order to converge to a solution. If it's too high, we might converge. We might never converge, right? We're going to diverge and never reach this minimum point that we're trying to have the model reach. But if the learning rate is just right, we can basically achieve the optimal learning swiftly, so very quickly, and with a minimum number of steps. Another important concept is the batch size. So this algorithm that we use to do the forward pass and the backward pass is called gradient descent. There are different types of gradient descent. One of them is the batch gradient descent. So if we have a data set with n samples, let's say 1,000 samples, then when we do the forward pass, we do it on the entirety of the data set, right? So look at all of the samples in the data set, do the forward pass, have the prediction, and then compare it to the correct value. So for all of the 1,000 samples in the data set, and then do the backward pass. So the problem with this approach is that the update now happens only after we see the entire data set, which means it's going to be very slow, right? So one pass is over 1,000 of samples. It's very slow, and in many cases, it does not converge to a good solution. Another type of gradient descent is called stochastic gradient descent, where instead of looking at the entirety of the data set, we just randomly select a sample from that data set. We use it to do the forward pass and the backward pass, calculate the error, and do the update. Now, the problem with this approach is that now you have too many updates, and the update itself is based on just seeing one sample, so it's going to be biased. And that's why we have a sweet spot between these two solutions. It's called mini batch gradient descent, where we still randomly select data samples from the data set, but now we format them or put them in mini batches. And the mini batch is usually in a power of 2 size, so 64, 128, and so on. And we do the training, so the forward pass, the backward pass on the mini batch itself. Now, once we have one pass over the entirety of the data set, that's called an epoch. And to train a network, we usually need many, many epochs, right? So to summarize, training involves having mini batches. We do the forward passes and the backward passes on the mini batches. Every forward pass and backward pass is called a step or iteration. But now, once you sweep the entirety of the data set, that's called an epoch, and you need many epochs to do the training. So finding the optimal batch size and the learning rate is very important. These are hyperparameters that you need to fine tune prior to the training so that your network is as accurate as possible, right? You get the best solution out of your network by tuning these hyperparameters. Now, how do we measure the success of the network? What is the metric that we need to look at in order to evaluate our network? There are two terminologies here that we need to avoid as much as possible, avoid seeing in our network or observing them in our network. One is overfitting, where the model is too complicated for the data set. So it's a very simplistic data set, but the model is too big. The model is not learning, but memorizing the data in that case. So this is what overfitting looks like. Let's say we have these orange data samples on this 2D plane, and we need the network to model this data set. So this blue line here is trying to model the distribution. And as you can see, it's overfitting on the training data. So that means if we have now testing data, new data that is unseen during the training, the model is not going to be very accurate because it just memorized the training data. Now, underfitting is the opposite case where the data is complicated, but the model is too simplistic. In that case, the model is not learning at all. It's not able to capture the complexity of the training data. So it's going to perform very poorly both on the training data and the testing data. So this is what we want to reach, the balanced state of training where the model is accurate on the training data, but it does not overfit, it does not memorize it. That means when we have now testing data, new data, it's going to be able to generalize on that data as well. Now, the example that we've seen is called a feed-forward network or a multi-layer perceptron. It's a very simple type of network that just takes numerical input, gives numerical output. But now, what if we have more complicated input types, right? For example, images. And computer vision is the subfield of artificial intelligence that basically deals with images. It enables systems to extract useful information from images, videos, or other visual inputs, and then take actions based on the input that it received. So we can do so many different tasks within computer vision. One of them is semantic segmentation, where if we have multiple objects in the image, we just assign different values to the pixels. So in red here, all of these pixels belong to the object cat, and then yellow would be grass, and green will be the tree. But we can also have a single object within the image that is of interest to us. So if there is one single object, we can perform classification. We've seen this example in the inference playground that was presented in the previous section. But also we can do object detection, so localization, not just classification, right? So classify the object, but also draw a bounding box around that object so we know exactly within the image where it exists. Also, we might have multiple objects, so same thing, right? Same object detection and instance segmentation, but now with multiple objects. So what sort of model architectures do we need to perform these computer vision tasks? Mainly, we have two architecture families, CNN architecture, which was introduced as early as 1989 with ConvNet and LeanNet. But until 2012, when AlexNet was introduced, um, that's really when CNNs proved that they can perform very well on computer vision tasks. So AlexNet was trained on the ImageNet dataset, a dataset with millions of images that was able to achieve very accurate results compared to the previous solutions, right? All the machine learning solutions that did not involve any deep learning. And since the introduction of AlexNet, we had bigger and deeper networks like ResNet, and GoogleNet, and so on. And the common theme within these architectures is the use of the convolution operation. Now, the other family is the vision transformer architecture. So transformer was introduced from the language side. So it was mainly a language model, but then the computer vision researchers found that this is a very good architecture. Why not use it for vision problems as well? So the VIT model was introduced around 2020. It uses attention now instead of convolution to do these different tasks, right? Either classification or object detection and so on. And vision transformers are now the state of the art, so they are more accurate than CNNs. But really, the best of the best solutions are hybrid architectures where we have the vision transformer, we have the CNN, both attention and convolution. We combine these operations together, and we get the best performance out of the models. Now that's mainly the computer vision side of things. What about natural language processing? Tasks that are related to language. So can the system also look at a text and then extract useful information and do different things with that information? So we can do machine translation, information retrieval, sentiment analysis, like rating reviews, are these positive or negative reviews, information extraction and summarization, and then question answering, like the fancy models that we use today, like the ChatGPT, the llamas, and so on. So what sort of architectures do we use for language? Early on, RNNs, recurrent neural networks, were used to do these sort of tasks, but the major limitation with RNNs is that they have a very short context length, meaning if we have a long sentence, the model will start to forget whatever text was introduced earlier. So it will only be able to focus on maybe 5 or 6 words in the past, which is a huge limitation. When transformers were introduced, and a paper that's called Attention is All You Need in 2017, the context now became much, much longer, right? So now we're able to focus on sequences that are as long as 1,000 words or longer. And from the transformer architecture, we got the BERT and the GPT models. And since GPT was introduced, now we have GPT-2, 3, 4, and 5, and so on. Now the context length can be in the millions, right? Millions of tokens or million of words. So the model has a very long memory. It can basically look at the earlier words in your sequence and still draw correlation, right, between the new words and the old words in your sequence. Now, with that complexity, right? So the model is now performing much better, but also the model is growing in size significantly, and the computation that is needed to train these models or perform inference on these models is also very complex. So just to give an idea, since 2019, the average size of the like best language model would be around 100 million parameters. Now we have models in the trillions of parameters. So yes, the models are getting much better, but also we need so much memory to store the model. We need so much computation to train and perform inference. Um, Now, one other popular architecture that is used today for both the vision and the language models is called the mixture of expert. This is not a new idea, but um, within deep learning for deep neural networks, it's applied in a very impactful way, let's say. The high level idea of MOEs is that we have ensample of models. Each model is an expert in a different topic. So, for example, in vision, different experts can focus on different subdomains. Like one expert can be an animal classifier, another expert can be a vehicle classifier, and so on. And then for languages, like different experts can focus on different languages. So now we have an expert in English, expert in German, and so on. And this MOE architecture is model type agnostic. So your expert can be anything really. It can be CNN, it could be an attention-based model, a transformer, it could be an MLP. Usually it's an MLP, multi-layer perceptron. We can take an example here, the DeepSeek V3, which was introduced last year, is a very powerful mixture of expert model. It's an open source, has 671 billion parameters, but only 37 billion parameters are active per token, right? So because we have different experts that focus on different subdomains, the token, the word that we're trying to pass through the model, will take um, a very unique path, which activates certain parameters in the model. So only 37 billion parameters are active, which means also the computation is much faster. And DeepSeek leverages multi-head latent attention. So I spoke briefly about attention, but they basically introduced this new attention mechanism where it makes the computation more efficient and more cost effective. And DeepSeek is designed for reasoning, but it also performs very well on logic tasks, pattern recognition, math, and so on. Also, if you want to deploy DeepSeek, it's available in FP8. Both the training is done in FP8 and the inference is done in FP8. So you can take advantage of this smaller version of the model that is quantized so that you can perform the computation and the communication much more efficiently. Okay, so
Nawras, there are
yes.
two questions on the Slack. Let me read it. It's one from Bob Lance. Is the growth rate of model size leveling off because we are running out of training data, running out of resources, such as compute, memory, communication power, etc., or for some other reason?
So I don't think the
Yeah.
model size is leveling out.
Yeah.
It is increasing in size still, but I agree that there is a limitation, right? That we'll reach a limitation where increasing the model size will not really improve the accuracy anymore. Um, the reason for that, as mentioned, yes, training data is a huge thing. So many of the researchers are now, instead of growing the model size, are focusing on the data. How can we make the data cleaner? How can we make it more representative of actual queries that will be fed into the model? Now, when it comes to compute, communication, and power, many optimizations are being applied and created. So one of these optimizations is MOEs, where instead of having the entirety of the weights active during the computation. You only have a subset of these weights active during the computation. But we don't really know the basically the extent of this model scalability trend that we're seeing, right? So if we keep increasing the model size, are we gonna keep getting better and better results? The answer is probably not due to the limitation of data. So, but I mean, it's an active area of research, so we'll see how it goes in the next couple of years.
Yeah. So the second question is from Thanos. Can the batch size choice contribute to overfitting or underfitting?
Yes, so the batch size can directly impact the overfitting or underfitting of the model. Um, Maybe I'll go back to this slide quickly. So with batch gradient descent, we usually see overfitting. Um, or I'm sorry, with batch gradient descent, we see underfitting. So the model diverges; it does not converge. Um, where the stochastic gradient descent, we see overfitting. So now the model is memorizing the data. So yes, the mini batch size will impact the conversions. That's why we need to choose both the optimal learning rate accompanied with the batch size.
Thank you, Nawras. Yeah.
Okay. Any more questions before we move
No,
on?
let's move on. There are no additional questions.
Okay. Okay. So now, like we know the general calculation or computation that is needed for DNN training. Why do we need parallel training? Um, as we mentioned, we have now larger and deeper models that are being proposed. So with the language models, we moved from the RNNs to transformers to BERT and GPT with its different versions. With vision models, we moved from AlexNet to ResNet, these CNNs to now vision transformers, which are larger, and the complexity of the computation, the attention operation is also more expensive. And these DNNs require a lot of memory in addition to the computation aspect. Um, Now, larger models um, will reach a point where we cannot fit them in the memory of a single GPU, which means we need to split them across multiple GPUs. So the community has moved to multi-GPU training, where we have multiple GPUs within the same node. So let's say we have the one computer and we can fit multiple GPUs on that computer, maybe up to 4, 8, or 16, but there is a limit, right? So this is called scaling up. We're scaling up within the one compute node. This is not sufficient, especially for the training. We have millions and millions, sometimes trillions of training samples. Model parameters can be in the billions as well. So that's why we need multi-node or distributed training, where we have multiple nodes, multiple compute nodes. Each compute node has multiple GPUs. So we have both the scale up and the scale out, right? Scale up within the one node, scale out across the system, so multiple nodes. Now, how do we achieve this parallelism? How do we enable a DNN to be trained on multiple devices? We have different strategies to do that. Perhaps the most common one or popular one is the data parallelism, where if, let's say, we have 4 machines, we place a model replica on each machine. So one copy of the model on each machine, exactly the same copy. Each machine will take different data samples and we'll process them. We'll do the forward pass, the backward pass. We also need communication. We need to synchronize these different machines so that they train together, right? We want to train one model and not 4 different models. This method is very good if we are able to fit the model and the GPU, but now if we can do that, we need model parallelism, where we split the layers of the model across different machines, or sometimes the layer itself is split across machines. Now, this method is very good for training out of core models, again, models that do not fit in the memory of a single GPU, but there is a problem with efficiency. As you can see, if we feed a sample to machine one, only machine one is active when it's processing that sample, right? Machine two and three and four are waiting for the output of machine one to continue processing things. So that's why we need hybrid parallelism, where we combine both model and data parallelism, or we perform some sort of pipelining where we keep feeding different parts or segments of the model different data samples. But with this model and data combination, we can have within the one machine, if we have multiple GPUs, perform model parallelism, sorry, and then across the machines we perform the data parallelism part. So mini batch gradient descent, we talked about this method. If the data set has million images, it can take forever to train on a single machine. Even if the model fits in the single machine, because the data set is so large, it can take up to like weeks or months to finish training. So that's why we need the multiple GPU setup. Now this is one solution where we have 5 machines. Each machine has all of the model weights. Machine one will take a different subset, a different mini batch of the data, do the forward pass and the backward pass. However, there is one very important thing missing in this solution, which is the communication part, right? So we don't want to train 5 different models on the 5 different machines. We want to train one model. Because if we don't do any communication, each machine will see its version of the data set, right? So it will be trained on that version, and the weights will end up being different on the different machines. So how do we do this communication? As I said, in the backward pass, we calculate the gradients, right? The direction in which we should change the model weights. Now, since each machine is seeing different part of the data set, it will end up having different gradients. So that's why we need an OR reduction operation. MPI OR reduce is what we use here to add together all of the different values. So for this weight and the matrix, and the weight matrix, we're gonna basically add all the cells that correspond to the same location. So 1 plus 1 plus 2 plus 5 plus 3, which is 12. And we see that it is the same across all of the machines after the OR reduction operation. So what we do here is we take the local gradients, the different gradients on the different machines, we perform the MPI OR reduce, and now we have the reduced gradients, the global gradients that are the same on all of the machines. Of course, after summing things, right? So after adding things together, we need to average. We need to take the average across all of the machines. Averaging can happen before the OR reduction operation or after.
So before we go there, there is another question, Nawras, on the Slack
Yes.
from Devang Patel. How do other parallelism would look like in case of MOE, and how their communication pattern would look like? And then the question is, do you have a slide that shows the parallelism being shown in multi-dimensions? I think we have those coming
Yes.
up.
So these will be covered on the advanced parallelism section.
Yes.
Now, for MOE specifically, yes, the communication pattern will be different. So instead of using or reduce, now we're gonna need to use all to all, because the communication pattern is different. The thing that we're communicating is also different. So it's not the gradients anymore. It is the activations. So I don't have a slide in this deck, but I can post a paper on the Slack channel after this section to basically explain how MOE communication happens exactly.
Yeah, that's all. Let's continue.
All right. So I talked about this MPI or reduce operation. Probably many of you is already familiar with what MPI is and what or reduce is. But this is the function that we call it will, the parameters that we feed into MPI or reduce is the send buffer, the receive buffer, the count, so how many data elements do we need to communicate between the different processes that are running, the data type, is it FP32, FP16, and the MPI operation. So are we going to do the sum or maybe the and or? In this case, we just use the sum because we want to add all of the elements together. And then the communicator, which is the group of processes that are involved in this communication process. So this is just an example of the send buffer before MPI or reduce and after MPI or reduce. And we see we start with local values. We end up with global values that are just added all together. Another question I see, what do the colors represent in this diagram? Looks like the horizontal stripes should appear in both before and after. So in here, so T1 is the tensor, right? T1 is tensor 1, tensor 2, 3, and 4. The different colors are different processes, right? So after the operation, we're basically I see that this the color scheme is slightly confusing, right? But then after the operation, these are the different sources of which the data came from, right? So because the or reduce operation can happen in different order, right? So it can happen in a ring algorithm, or it can happen in like a reduce scatter all gather. The source of the data can come from different locations, basically. So that's why we see this color ordering. I hope that answers the question. Okay, so moving on, let's put all of this together. We have this data parallelism scheme where we explain that we need to have a model replica on each GPU device. We perform this in 3 steps. First of all is the data propagation. So we have this batch of data, we break it into mini batches, right? So each batch is fed into a different GPU. We start exactly with the same parameters, so same values for the different parameters. And then we perform the forward pass, the backward pass. Now we end up with the local gradients on each different GPU. These are different gradients, right? So we need to perform MPI or reduce to combine all of the values together. So we sum them up, and then we or reduce will redistribute or broadcast all of this back to the global gradients. These global gradients are exactly the same. So only when we have exactly the same gradients on each different GPU, then we perform the weight update, right? So now this is just one iteration, one training iteration. So this basically global gradients will update the model parameters, but see, like in the next iteration, we have exactly the same model parameters to start with. So this is just like one part of the data that we're seeing. We're going to perform this many, many times until we pass on the entirety of the data set. And then this is one epoch. Now, when we pass the data set one time, we need to perform many epochs. So you can see that MPI or reduce is called many, many times during the training. That means we need a very efficient MPI or reduce process. Because we're calling it many times, we want to make sure that it is not the bottleneck, right? It's not causing a slowdown in the training. Any questions on this figure before I move on?
Let's continue.
Yeah, this basically summarizes data parallelism. And one thing to keep in mind, so there was a mention of the batch size, and Does the batch size affect the conversions of the model? Does it make it overfit or underfit? This is an example, right? So when we train, let's say, a ResNet model or a vision transformer on a data set, at one point, if we increase the batch size beyond that point, so in this case 8K, so 8K samples, if we increase the batch size beyond that, we start seeing degradation and the validation error. So the validation error increases, which means the model is not performing as well if we were to train it with a smaller batch size. So it is bad for accuracy, the large batch size, but it is good for scalability and speed because now we can process more samples across our system, right? So it's good for scalability. We can see that the training time will decrease as we increase the number of GPUs and keep the local batch size the same per GPU, but the accuracy will drop. So this is a hyperparameter that we need to tune prior to the training. Also, there are some advanced solutions. There are optimizers that will enable us to um, push this point further, right? So now instead of seeing the degradation at 8K, we will see it maybe at 128K, which will give us more room to spread our workload across more devices. Now, when we talk about the model size, we say that the model size is increasing. What do we mean exactly by that? Is it just only increasing the number of parameters? It is one aspect of the model size, right? So the weights on the edges or the parameters, this is when we increase the width of the model. So within the one layer, we have now more parameters. But also we have the model depth aspect, right? So if you have more and more layers, even if we don't have more parameters, if you have more and more layers, that means there is a longer computational sequence. There is a longer dependency. This is the inception model. The inception model is just the same block repeated many times. So we take this block and we repeat it over and over. And we see if we increase the depth of the model, we get usually better accuracy. So that's basically like the two dimensions of the model size that we talk about. Now, model size will decide the number of GPUs that we need to use, but it also decide the amount of data that we need to feed to the model. So if we have a small network and a small data set, we're gonna achieve very good accuracy. So the small model is sufficient, it's good enough for training on the small data set, and we can do it on the single machine. So we don't need multiple GPUs. In fact, multiple GPUs can impact the performance in a negative way. So we can just do it on the single machine. Now, if the network size is large, we can use the multi-GPU or the distributed training, even if the data size is small, but we might also overfit. So this is something to keep in mind. If the data size is large, but the network size is also still small, we might do it on the multi-GPU or distributed, so across multiple nodes, but we might risk the underfitting. So distributed training becomes very, very useful when both of these conditions are applied. Both the network size is very large and and the data size itself is also very large. That's when we need the multi-GPU, multi-node setup to enable us to train the model in a short amount of time. One last thing to keep in mind is that we have two flavors to doing gradient descent. One of them is synchronous, the other one is asynchronous. So as I mentioned, the gradient will tell us the direction in which we need to apply the model update. But then when do we exactly perform this model update? If we have different machines, can we have each machine perform its model update at a different time? Meaning we don't need to synchronize all of the machines at any given moment. We can have them synchronize at different time steps. So this is what asynchronous training is. And asynchronous training will give us higher epochs per second. So we can process more data per second because now synchronization is not very critical, but it will give us low accuracy per epoch. So we need many epochs to converge to reach a good solution. We have the synchronous training, which is the example that we saw where we have this blocking operation, MPI or reduce. We only perform the parameter update after seeing basically that all the gradients are the same, right? We have the global gradients. But there is also solutions in between where we perform the async SGD with stale gradient handling. So because now there is a gradient mismatch, we need to mitigate that. So there are some solutions that will basically reduce the degradation and the accuracy. But I should say that most of the training techniques that are used today are synchronous. So we don't use the asynchronous training as much. Synchronous will guarantee that we are getting exactly the same output as if we were to train on the single GPU, right? So we're not impacting accuracy at all. At the same time, we have this small price to pay when it comes to synchronizing the data, the gradients across the different models.
So Nawras,
Yes.
there is one question from Nick Sarkauskas. There is one gradient per parameter, right? Does that mean the size of the all reduced and data parallelism is the number of parameters?
Yes, exactly. So yes, there is one gradient per parameter. Now sometimes we use the mixed precision, right? So sometimes the parameters are in FP32, but the gradients are in FP16. So the gradients will be half the size, but the number of elements is exactly the same.
Yeah. So we'll take so might be, I discussed with the organizers, we'll take a 20 minutes break in few minutes, but might be let's Nawras introduce how people will create the
Sure.
accounts
Mhm.
and then let them create an account, go over the hands-on a little bit. We'll take a break and then come back. Okay.
All right. So this slide will just set up for the lab. So you can go to this link, go to OSU
Yeah, you can
DL
share that
tutorial.
also.
So yeah, we can post that in the Slack channel. Let me open it. And so here we have different accounts, different usernames and passwords for each account. I've claimed the first account, so please choose a different account in the sign up sheet. Just type in your name to reserve that account. And let me go back to the slide. Yep. So to access the system, just open a terminal, do SSH, and then put the username in the first half. So RI2 to TUT01 here. 01 is my account, so just update it with the number of the account that you claimed. And then enter the password. It will take you to this directory on the system. The Hatay High DL tutorial. We have 2 labs, and then there is a README that will explain exactly what commands you need to run for each of these labs. Please do not copy and paste things from the slides because the commands are not going to work. Use the README. You just need to copy and paste things. I'm going to walk you through the process once we get to that point.
Yeah, so I posted the link, Nawras, on the
All right.
on Slack. So I think Nick is here. Let's why don't we take a 10 minutes break? I think Nick, this is like I think 10:09 Pacific. So we'll join back in 20 minutes. 10:30 Pacific. Let me post that also. So Nick will be playing some videos and all. Okay, welcome back, everybody. I think we have some of the Slack discussion going on the accounts and all. So let's get started. I believe the basic account issues are resolved, or still people are seeing some permission error, I think. Nawras, you can see the chat.
Got an error opening. So, David, could you try a different account? See if the problem is still there. Bob, you're running the train bird signal. Okay, so we'll get to that and we'll see why this error is happening exactly. Yes, it is intentional. That is expected.
Okay.
No
Yeah.
worries.
So let's then share the slides. Then
Yes.
we'll go through the exercises. Okay.
Okay. Let me see if I can. Just 1 second. Okay. Okay. Can you see my screen like side by side?
Yes. Yes.
Okay,
Good.
perfect. So the first lab is on the subject of DNN training using PyTorch. So the objective is to uh, uh, train on a single GPU and then perform distributed training and see the sort of performance that we get for PyTorch on a single GPU. Then for task 2, we're going to do PyTorch on multi-GPU. I've already ran the experiment on my end. So I SSH to this account. I basically copied the command from the README file and executed it. And as you can see, the model here is ResNet 50 with a batch size of 64. We're running on one GPU. And this is a synthetic benchmark, meaning we don't really care about the data and the accuracy. We're just looking at the throughput. So what sort of performance do we expect out of this model? On this GPU, in here we have V100 GPUs. We see around 336 images per second per iteration. So at the end, we're gonna get the average across all of the iterations, the 5 iterations. And we see that there is a small, basically, variance from iteration to iteration that is expected. Now let's see the 2 GPUs experiment. So for those of you who are running, let me just tutorial 01. Let me open the README. So all I did is just for the first experiment, I copied this and pasted it. Second experiment, copied this and pasted it. So for the second experiment, this is the multi-GPU with PyTorch. So exactly the same model, same batch size, but now we see that the number of GPUs is 2. You see that there is a small degradation in performance per iteration. So instead of getting the 336, now we're getting 325. But now the combined throughput on the two GPUs is 651. So this is near linear scaling. We're getting around 10% or less overhead for performing communication between the GPUs. So remember, we said that we have this or reduce operation. Or reduce is performed on the number of parameters, like Nick mentioned, right? So the model size for ResNet 50, this is the amount of communication that we need to do during every iteration. Now, the third experiment is on TensorFlow. So with TensorFlow, again, exactly same setup. We see that the throughput on the single GPU is slightly better than PyTorch. So now we're getting 342 images per second as opposed to 336. So like we got maybe 8 images per second in throughput with TensorFlow. This is expected. So different frameworks, different DL frameworks will have different implementations for the same model. So for the ResNet 50, you might see better performance. Maybe for a vision transformer, we'll see that PyTorch is doing better. So it is model dependent, but more or less it is very close in terms of the throughput. And finally, here we have the TensorFlow on 2 GPUs. In here, we see 632 on the 2 GPUs compared to 651 for PyTorch. So PyTorch is slightly more efficient when it comes to multi-GPU experiments. And by the way, this is running on top of Horovod. So Horovod is a middleware, is a communication middleware that sits between the DL framework and the underlying MPI library, and it will implement data parallelism. And it's compatible with both PyTorch and TensorFlow. We're going to cover the different layers in more details in the advanced section. But this performance should be consistent. So share your numbers on the Slack channel. Let me know if you're able to run any of these experiments or if you have any problems. Let me share the slides again. So yeah, you should expect around 1.9x the performance on 2 GPUs with PyTorch. With TensorFlow, it should be around 1.83x. So just to summarize this exercise, we ran the synthetic training benchmark from Horovod on the single and multiple GPUs. Now Horovod can underneath use MPI, glue, nickel, or any communication library. You'll see different performance with different libraries depending on how efficient they implement the ORID use. Now the library that we use is EnvaPitch Plus with CUDA-aware designs to deliver this near linear speed up on multi-node, multi-GPU training. And if you are interested in installing this high DL, high performance deep learning stack on your system, we have a full user guide to walk you through the installation process. So again, let me know if you have any questions on Slack.
Yeah. So there are two things. I think there is a quick question, I think from Thanos. Is CPU only training in multi-node environment still relevant, or has GPU-based training become the standard practice?
So GPU training is currently the standard practice, but if you have access to many CPUs, a system with many CPUs, you can still take advantage of that. It will deliver reasonable performance. In fact, we have some numbers to show you in the advanced section on both the CPU and the GPU and see how these two compare to each other.
Yeah. And might be since some people saw that out of memory error, so Nawras, you can
Yeah,
give some insights there.
so this is in lab 2, right? So you ran those experiments in advance. It's okay if you see the out of memory error. We're going to talk about it and why you are seeing that error. So it is intentional. It's part
Yeah.
of the exercise.
Just to hold on a little bit more time. Okay. Okay. So Norris, thanks. So now let me share the next two sections I'll cover. Um, okay. You can see my slides and all.
Yes. Yeah, we can see them.
Okay. So far as you saw in the first half of the tutorial, I mean, we started with like 100,000 feet level, gradually went down, understood the basic concepts, and then went into the data parallel training, and then tried to do this hands-on so that you get a feel for how the data parallel training works. But as we motivated, I mean, this field is advancing so fast, the model sizes are becoming larger, people want to train, reduce the training time. And this is where I think we need that advanced kind of parallelism. But before we go there, we just want to give a very short overview. Many of you might be knowing this. If not, we'll try to catch you up. That is the whole idea of this section, just to take a look at what is happening with respect to hardware, software, interconnect. And as I indicated earlier, just in the today afternoon, we have another half a day tutorial on high performance interconnects. We'll go into much more deeper in that tutorial. Here we'll remain a little bit. So if you take a look at any commodity modern HPC cluster, I mean, this is what you will see. Like these are, let's say, some of the top 500 systems. Multi-core, many-core processors, networks like InfiniBand, Slingshot, Rocky, coming accelerators like AMD or NVIDIA, and also the SSDs, RDM-enabled SSDs, and all these things are coming. So these are the typical kind of the components, not only on the on-premise system, but exactly similar things are also happening on the cloud system. So in that context, let's just get a little bit of overview of the hardware and software, whatever is relevant to the high performance distributed training and inference. That's what we'll talk. We'll not go into more details here, but in the afternoon tutorial, especially on this interconnect, we'll go much more into depth. So just to give you perspective, I mean, as these clusters are coming, of course, everybody wants to deploy a very large cluster. You must be hearing like people are trying to deploy like a 1 million GPUs, not only been on premise, across regional different areas. In fact, earlier this week, we do an annual MAPIC user group conference. We had a keynote talk from Meta. So they were saying they want to deploy even a 1 million GPUs spreaded over 100 kilometers. Okay, so it is not just like everything is in one data center, but they want to connect into large data center. So in that context, of course, there is a lot of different networking technologies are being used, InfiniBand, Omnipath, and especially this Rocky also is coming up, Ethernet, Ultra Ethernet, Scale Up Ethernet. So there are a lot of these things coming. We'll talk in the afternoon. But the broad idea is that all these interconnects are trying to deliver very low latency. Okay, like a few microsecond, high bandwidth. If you go to the very latest NDR, like 100, 400 gigabits per second, and already the discussion is coming as an 800 gigabits per second. But more important, and this is what we'll discuss much more in detail in the afternoon tutorial, is the low CPU overhead for protocol processing. Okay, so the idea is that I mean all these networks are being designed, but then once you start building the software, you don't want to spend a lot of time in doing the protocol processing. You want to keep the CPUs idle or not idle, like available for actual your training or inferencing. And this is where a lot of actions are taking place. There are a lot of software stack like UCX, the OFI and all that are coming up. This is just trying to see over the years, like InfiniBand, if you remember, introduced at 2000, almost like 25 years back with the SDR, DDR, QDR, and currently we are in this range. NDR, and then there is a plan to go into the XDR and GDR range. Now, of course, there's a commodity direction is going on, but there are also very dedicated systems are being designed. And one of such thing is, of course, the Google TPUs. They have gone through a generation, TPU1, TPU2, TPU3. So the broad idea here, as you saw, the underlying to the distributed training is this matrix vector, matrix matrix multiplication. Okay, so that is the key thing. And instead of like running it on a traditional x86 platform or an ARM, the question is, can you actually design this in a much more efficient manner? So that's what TPU has done in a very tightly integrated manner, similar to like also some work took place on this IPU, like intelligent processing unit. So if you can customize your hardware and bring much more denser integration, you will be able to run all these things much more faster. So actually, Intel worked with Microsoft. So here, Microsoft Azure had some of these IPU instances. Intel also had a big project. I mean, some of these are gradually going down and some are going up, some are going down, but we want to give you a perspective of what has happened in the field over the last several years. So this Intel again acquired the company called Havana Labs, and they have very dedicated. Again, you can think of it as like a instead of a NVIDIA GPU or AMD GPU, they have dedicated chips which will try to do this kind of the training. And of course, there is also a very big company called Cerebras. You might have heard of, like what they have is a very wafer scale engine integration. Think of like this tensor core, just like what we hear from NVIDIA, but this contains like almost 400,000 sparse linear algebra compute. They call it like a SLAC course. And within a single chip, as you can see, the very largest chip here, they introduced in the Hot Chip 20, the very first one, it has 2.6 trillion transistors, okay, and almost 850,000 cores, okay. They had a Cerebras 1, now they have gone to Cerebras 2, Cerebras 3. So think of like when these model sizes are becoming larger, instead of distributing it across multiple nodes, if a single system can actually have everything in their own memory, they will be able to do much more faster training and inferencing. So that is the kind of, I think of very leading edge systems which are being designed. But irrespective of the hardware, of course, there is a need for the communication middleware. And this is where a lot of actions are taking place. Let me quickly provide you an overview of what has happened, where we are. Again, in the afternoon tutorial, we'll go into much more detail in this part. So if you take a look at very high level overview of the parallel programming, if you think of like a current node these days, there is shared memory within the node. The most common one is this distributed memory model. Okay, so every node has their own memory. When I say node, it can have CPU, GPU. Within that node, there might be also the unified memory concept. But then once you go outside, this is where you need to use some kind of a communication stack. And mostly MPI has been the most common one from the HPC side. And then it is moving into the AI side. And of course, in the field, there was like some partition global address space was introduced in the mid 90s, became very popular. It is still there up to a certain extent. There was a SMEM model, open SMEM. And in fact, some version of that has now come back. If you take a look at NVIDIA stack, it's called NVIDIA SMEM, NV SMEM. Okay, so those kind of programming models are being used to orchestrate this communication. Okay, and we saw this example, like at least the distributed data parallel training, this all reduce. We saw the example, and this is where, let's say, everybody has some SGDs, some of the errors, then you need to put them together. So that means that the network plays a very important role, and it performs this all reduce. Of course, all reduce depending on the data size, message size, number of GPUs, number of CPUs. There are so many different algorithms which have been proposed in the literature, and this is where everybody is trying to optimize. Okay, MPI is trying to do it, Nickel is trying to do, RICL, XCCL, everybody is trying to optimize these kind of collectives. And So far, we got exposed to already use, but I believe there was a question, and I think Nawras answered like with this MOE. People are exploring other collectives like all to all. Similarly, all gather also is being used. So gradually, as I said in the in the first half, these collectives have been there in the MPI world for last 30 years, but gradually the AI field is discovering these things. So the question is, okay, how do we actually optimize all those? So here I'll give an example here, and later on we'll see. This is the MHAPIS project I mentioned. If you remember going back in the COTS project, they used our MHAPIS. That time there was no communication stack which can actually communicate. We started this project almost in year 2000, October year 2000, when InfiniBand was announced. Prior to that, in my group, we were working on Myrinet Quadrix. Those are the interconnects, if some of your old timers might be remembering. But when InfiniBand came, there was no software stack. It was purely hardware. There was a standard. Uh, we were the very first group in the world to jump in and have actually an open source MPI version. And we demonstrated in the supercomputing 2002, almost 23 years back. And since then, I mean, I am very proud of my team. We have been continuing this project. It is continuing for 24 years now and counting. And not only we have InfiniBand, we support all interconnects. Omnipath, iWarp, Rocky, even AWS, Elastic Fabric Adapter, OPX, Broadcom Rocky, Intel Ethernet, Rockport Network, Slingshot, everything we support. And of course, in the again afternoon, we'll go into more details here. And currently, this is like being used by more than 3,450 organizations in 92 countries. If you take a look at these are registered users. If you go to the users tab of the Mapis page, you can actually see how all over the world people are using it. And I'm very proud to say that we have almost like hitting very close to 2 million downloads just from our website. Of course, the stack is a part of Red Hat, SUSE, OpenHPC, SPAC. It's very hard to keep track of those downloads, but these are the downloads from directly from our page. In addition to MPI, we also have a sub project there called OSU MPI micro benchmarks. That is also very extensively used, called OMB, to evaluate performance of all these collectives, the network, point-to-point communication, collective communications, etc. And and of course, these stacks are being used almost like for the last 20 plus years in a lot of top 500 systems. Now, what is important here, this is coming back to the question, even though like 20 years back, everybody was using only CPU system, but the GPU came into the picture. And I don't know how many of you have heard of this, like a CUDA aware MPI or GPU aware MPI. In fact, we did that in our group. If you go back, ISC 2011 paper, we did a joint collaboration with NVIDIA and Mellanox. That time they were separate to bring the idea. So let me explain. So if you think of it like a very simple node. Of course, nowadays the nodes are much more complicated with more adapter, more GPUs. But if you see a simple one, like I have an IB, the most of the time programming, what happens is you give the code to the GPU, GPU performs the operation. But if you want to send from here to other GPU, you have to take it through CPU and then send it out. Okay, that was the traditional one. So here what we introduced this GPU direct RDMA or CUDA aware. The idea is that if I have to send data from this GPU to this GPU, instead of going through CPU, I can actually directly send the things from the over the network. So that's what you at an MPI level, you can just say MPI, just like in the host memory, you say you give a host memory buffer. So now you can actually give a device buffer and say that okay, MPI sends it from this buffer, and the receiver it receives. And that actually changed the way this in HPC applications used to get programmed. And of course, now this has actually gone into even all the collective libraries and all. So you can see like some of the animation. And when we introduced that, it actually led to much more higher performance and higher productivity. Okay? And especially if you can see here, like earlier, like you have to take the data from GPU to memory, doing a CUDA mem copy, communicate, and then do another CUDA mem copy, you used to lose a lot of performance. But by directly sending from GPU to GPU over the network, we are able to significantly reduce. Okay, and this trend is still continuing with any even modern processors are becoming faster, GPUs are becoming faster, CUDA overhead is coming down, but still this gap continues. And here we demonstrated like a, if you see here, like a, instead of like a around 18 microsecond, we can actually reduce to 1.85 microsecond, almost a factor of 10x reduction in latency, and then almost 9x and 11x improvement in the bandwidth. So that was happening in the MPI domain. And then gradually, as the field got more attraction, so this is where NVIDIA introduced first time called Collective Communication Library, NCCL. So the NCCL one was efficiently only inside within a single node, and then they extended it into the NCCL 2. And nowadays, of course, there are very complex topologies. If you go to the DGX or even the NVL72, the machines are coming. There's so many layers you have to communicate. You have NVLink, you have the external networks, multiple interface, multi-rail, and this is what NCCL has been improving the collectives. At the same time, MPI libraries are also improving the collectives. And we'll show you some results in the next section. And especially in our MAPH, we are able to deliver a kind of a vendor neutral manner. If you totally depend on MPI collectives, you don't need NCCL, you don't need RICL. You can just use their GPUs, but purely through MPI communication. And when I say MPI communication, it includes like a PCI communication, it includes NVLink, whatever is the topology allows, and delivers very competitive performance, and even sometimes better than the what is available there. So we'll take a look at some of these things in the next section. But more importantly, we'll go into a lot of details along this direction. If you're interested, please feel free to join the afternoon tutorial. So with this,
Dr. Panda, there are
yeah,
a couple of questions on
sure,
Slack.
go. Yeah,
So one of them is Bob is asking, this sounds like NVIDIA's GPU Direct and NVLink. I believe he was referring to the like GPU aware. Yeah, this slide.
Yeah, the same thing. It is actually what I'm saying. This concept started in 2011. The idea that GPU Direct RDMA, we actually worked in the very beginning with NVIDIA and Mellanox. So they designed the driver, we put the software on top of that. Okay, so please take a look at the ISC 2011 paper, and then that idea, that's what I'm saying, has been being continued. But that is where the origin, it started in 14 years back.
Yeah. And then another question, I assume PyTorch is using NCCL. Is MPI used for AI ML workloads or mainly for other HPC apps? How well does MVPitch work on GPUs versus NCCL, XCL, and so on?
Just wait for the next section. We have all those exact results for you. Okay, so we'll try to show you these results. We have actually, what we have done basically, when we say people use MPI, it's not that the end users will use MPI. If you are using something at the PyTorch, you remain on the PyTorch level. But from the PyTorch, just like the PyTorch takes to NCCL or RICL, we direct the communications to the MPI. Okay, and that is the version actually is publicly available. Anybody can download. We have a GitHub, and you can download and build it on any hardware. Okay, or any interconnect and all. Because if MPI supports, our MFP supports any combination of CPU GPU interconnect, you should be able to run your DL applications on top of PyTorch using that framework. We'll go into more details. Just wait for a few more, I think 10 more slides. You will get it. Any other questions?
There is one more question. So I believe the Cerebras one, Alex answered that. Then it looks like we're seeing large scale up fabrics. For example, we heard about UA-Link, 1K nodes, as well as optical fabrics such as micro LED, as well as CPO with circuit switches, NVLink switches, and so on. How do these fit in? And we have also HPC WAN emerging. Do RDMA fabrics like Rocky and InfiniBand work over WAN?
Everything. There are a lot of competitive solutions are coming up. And so obviously these days, if you see, there are two kinds of directions: scale up and scale out. And scale up, of course, NVLink was the thing. Nowadays, UA link is coming, scale up Ethernet is coming, and in the scale out, InfiniBand, Omnipath, Rocky V2, Slingshot, all those are competing. And I mean, Ultra Ethernet is trying to combine both. Okay. So then the question is, based on the system, now the question is, okay, how do we take care of the training? So this is where the software matters. Okay, so that's what I indicated. Different companies are coming up with different solutions. NVIDIA is putting their nickel library, AMD is putting their nickel library, Intel is putting their, let's say, XCCL library, one API. So, and other vendors are providing their own stack. And similarly, what we are trying to provide is the API layer, okay, which gets linked to PyTorch. So all these, even nickel gets connected to PyTorch, or nickel gets connected to PyTorch. So answers to all these things in great detail is in the afternoon tutorial. Okay, so if you're interested, please join and we'll go into more details on that. Okay, any other questions?
No, I believe
Okay.
these are all the questions.
Okay, so then now if you see, so very high level, I mean, we saw some examples, but let's say the broad question you will ask, like let's say HPC has been there. How do we use the HPC for machine learning, deep learning, or even data science, and take advantage of these heterogeneous resources? So when I say heterogeneous, it is like the CPU, GPU combinations, and they come in many forms. Like you see very dense, like we have 8 GPUs per node. Sometimes a lot of GPUs on the single rack, or you connect into multiple racks. At a conceptual level, research is happening along 4 directions. So that's what I want to highlight here. And in the next section, we'll actually link to this solution. So if you take a look at like even traditional HPC applications, I mean, you have a machine, let's say I'm trying to run WRF, or I'm trying to run OpenFOAM, or any of these traditional HPC applications. With these, the broad idea is that, okay, these applications have some memory requirements. There are some computation requirement. There are some communication overhead. So how do we actually try to optimize? That's what the HPC field has been going for the last 30 years. Now, exactly the same things are happening here. Okay. So if you take a look at, let's say, any of these frameworks we talked earlier, like a Cafe2, TensorFlow, PyTorch, if you go inside, this is where we saw like we have to have model propagation, forward pass, backward pass, gradient aggregation, and the size of the model. So all these requirements still exist, but in a different form. It is just coming at a framework level now. So if you can optimize that framework, let's say PyTorch with this underlying layer, then the end user should be able to take advantage of it. So this is kind of the very one direction of work taking place. So then the second one is the communication runtime. Okay, so let's say we have, like we saw this, the forward pass, backward pass. We want to do all reduce, all to all. These collectives were there in the older MPI. Now the same thing has to come here, but then the same ideas exist. Like if I have a 1 million GPUs, how do I do all reduce? How do I do all to all? Okay, the same challenges exist here with respect to distributed training, and now also becoming very similar in the inferencing. Like we touched a little bit saying the MOE models, it requires all to all. We'll take a look at that later on. The third direction is actually how do you implement those collectives? Okay. And this has been a big challenge, and a lot of people are working on, including us from an MPI side as well as from others. The difference in the MPI already was there 30 years back, also it was there, but most of the HPC application, if you remember, they were doing in an iterative manner, and at the end of the iteration they do all reduce. But that all reduce message size is very short, only 4 bytes or 8 bytes. But now in the AI world, the same concept is there, but the message size has blown. It is like you are trying to do an all reduce on 4 gigabytes, okay, or 100 megabytes, okay, based on the model, based on the system size and all. So that means there is a big challenge here. How do we implement these large message collectives? Okay. And then, of course, how do we take advantage of the GPU Direct RDMA, the CUDA awareness we talked earlier? So that is the third direction of research. What is happening when I say research development in academia as well as in industry is taking place. And then the fourth one, which is taking place like a co-design. Okay, and of course the concept of co-design has been there even in the HPC. Like let's say you have a WRF application, you want to run it faster based on some CPU type, interconnect GPUs. How do you do? Exact same idea is also coming here. Okay, so might be I have an LLM training here, and below that I am using PyTorch. Then below that, let's say either I am using Nickel or MPI, and then below that I have the actual hardware. So how do I co-design all these stacks together at the runtime level and exploit at the DL framework level so that the entire application runs faster. So these are the kind of the very four broad directions I just want to highlight so that next time when you read a paper or see a solution, and we'll give some sample solutions here or approaches together with a lab too, so that you can actually correlate saying, okay, whether this is happening in the direction one, direction two, direction three, or direction four. So that is the whole idea of this kind of a the approach we are trying to do. Okay. Any other questions here? Otherwise, we'll keep moving to the advanced distributed training, and we'll take a look at some of the advanced parallelism, and we'll also do lab two, and then we'll move into the inference, and then go into some of the open issues and challenges, and then conclude. Are there any other questions,
No
Nawras?
questions so far.
Okay.
That's
So
fine.
then you can switch over, and then
All right.
let me stop and
Okay. All right. So yeah, so in this section on the advanced distributed training, we're gonna look at some of the more involved data parallelism solutions. We're gonna look at some numbers, see the different options we can configure the distributed training stack. Again, a reminder, data parallelism only works if the models fits in the single GPU. Then we're going to look at the model and hybrid parallelism, such as 0 and 3D parallelism, where we distribute the model weights and parameters across multiple GPUs. So this is the MVPitch or MPI-driven infrastructure for MLDL training, MPI 4DL. This is basically this section is what we ran our lab on earlier. So we start with the MLDL application. Under that, we have TensorFlow, PyTorch, MXNet. So the DL framework, we use both PyTorch and TensorFlow. And then under that, we have the distributed training middleware. In this lab, we used Horovod. And then under that, we have the communication library. So it could be an MPI library or Nickel, Brickle, Glue, different communication backends. In our stack, we use MVPitch for CPU training and MVPitch Plus for GPU training. On the other half, this is mostly directed to the PyTorch framework, where the distributed middleware can be either torch distributed or deep speed. And the backend for communication is again MVPitch for CPU, MVPitch Plus for GPU. Right now, Torch Distributed is the most popular and supported distributed framework in the community. So most of the new models, you'll find them strictly only supported with Torch Distributed. If you would like to learn more about this stack, we have both a GitHub repo and basically a guide, a user guide, so that you can install the stack with these different configurations. We have a recent release of this stack, IDL 2.0. It supports PyTorch 2.7.1 and later versions. And it supports the native DDP, distributed data parallel training. since the MPI library itself is optimized for both a CPU and GPU, you're gonna get efficient large message performance, whether it's or reduce or other operations. Um, and the or reduce itself is implemented using the GPU direct ring algorithm and also the two-level multi-leader algorithm. It supports fork safety. So fork safety is very important in the DL frameworks world because the framework itself will use multiple threads to perform data loading on the CPU. So the MPI library needs to be aware of that. Um, and the stack exploits efficient large message collectives that are implemented in the MVPitch Plus library. So we have an open source PyTorch version with advanced MPI support. You can download it from the GitHub repo and install it. Um, so the advantage of using this stack is that it's vendor neutral, meaning whether you have like NVIDIA GPUs, AMD GPUs, different interconnects, InfiniBand, Slingshot, and so on. This stack is neutral. It's gonna support all the different combinations. And then these are the software stack details. So CUDA 12.x, ROCm 6.x, and as I said, PyTorch 2.7.1 and later versions are supported. So let's look at some of the numbers. This is on the Vista system with Grace Hopper 200 GPUs. So in here, we're using Torch Distributed. The application is a GPT-2 model training using NanoGPT. So the Vista system consists of single Grace Hopper nodes. So each node will have a single Grace Hopper super chip with ARM cores for the CPU and then the H100 GPU on the GPU side. And then this is the interconnect, NVIDIA NDR InfiniBand. And as we can see here, we're comparing Nickel and MVPitch Plus. This is the time per iteration. So we go from 1 GPU to 64 GPUs. And we see that the time per iteration is scaling nearly with both Nickel and MVPitch. So Nickel will be installed by default with the PyTorch. But if you were to use basically MVPitch Plus, you can um, use it with these different combinations that we talked about earlier, and you're guaranteed to get same performance or better performance. So this is, for example, on a different system, Frontier. In here we have AMD GPUs MI 250X. And here we're comparing Rickel and MVPitch Plus 4.1. This is within the one node, we have up to 8 GPUs. We see that the performance is more or less the same. As we go beyond the single node on 16 GPUs and up to 128 GPUs, we see that out of the box MVPitch Plus will give you slightly better advantage in here. So both the two previous examples were with the Torch distributed. These are some numbers with Horovod, and this time we're looking at a vision model, not a language model. So this is ResNet 50 on the Summit supercomputer with up to 1500 V100 GPUs. We're training on the ImageNet dataset, around 1.2 million images. The time per epoch, so basically to swipe the entire data set is around 3 seconds. To train ResNet on ImageNet, we need 90 epochs, so the total training time is 4.5 minutes. If we were to do that on a single GPU, like you can imagine this taking weeks, if not months. But if you have access to many GPUs, you can perform this in only 4.5 minutes. So there was also a question earlier about CPU, how practical are CPUs? Are they still relevant for AI workloads? The answer is yes, if you have access to many CPUs. So this is on the Frontera system. We see the scaling from one node up to 2K nodes with the MVPitch 2 library. In here, we have exactly the same application as the previous slide. So the ResNet 50 model on the ImageNet dataset. And it delivers around 260,000 images per second. So you can do the full training, the 90 epochs, within 7 minutes. So to compare, 4.5 minutes on 1500 V100 GPUs, and this is on the like Frontera system, 2K nodes, around 7 minutes. And I would say this is still applicable um, to like the most recent CPU architecture, the most recent GPU architecture. You can expect like something similar in terms of the performance. One more basically solution when it comes to DNN training with distributed data parallelism is that what we've observed recently with the relatively smaller, lightweight models on the advanced A100 and H100 GPUs, they underutilize the GPU resources, the compute resources. So you'll see that the CUDA core utilization is around 40%. At best, it's like 65%. So since these models are small for these larger hardware devices, you see that there is a lot of resources sitting idle. So the solution that we proposed in a IPC paper a couple of years ago is that instead of having one replica of the model per GPU, what if we place multiple replicas of the model on the same GPU so that we can um, increase the parallelism, increase the workload that we can perform in parallel on the GPU itself. And with that, we can look at the ResNet 18, the ShuffleNet model. On 16 GPUs, we see up to 30% and 62% improvement. So this improvement will be different from model to model. And if your model is large enough, you're going to stop seeing any improvements. So this will mostly work on the um, lighter models. Now, later on, we're going to look at these very large models. How can we deal with those? So we're looking at both ends of the spectrum. So model and hybrid parallelism. We'll start with zero and then move on to 3D parallelism. So zero is an optimizer designed by DeepSpeed from Microsoft. Later on, it was adopted by PyTorch, called FSDP, fully sharded data parallelism. And I have a nice animation here, if I can play it. Okay. So zero four-way data parallel training using optimizer state, gradient, and parameters. So we talked about parameters, we talked about gradients, and now we also have optimizer states. These are extra parameters that we need to keep track of during the training, only for the training. So if it's inference, we don't really need the optimizer states. And in this example, we have a transformer model with a data set. The data set is going to be distributed across 4 GPUs. And these are the different layers of our transformer model. Now here in green, we have the optimizer states. In orange, we have the gradients. And in blue, we have the parameters. And in here, we're doing mixed precision training, which means we're going to save copies of the parameters in FP16, the gradients in FP16, but also we're going to have an FP32 copy for both the gradients and parameters and extra optimizer state parameters. So all of this huge green block is only needed during the training, but it takes the most memory. So this is the regular data parallelism, what we're seeing right now, where we have the entire model, all of these blocks saved on each GPU. As you can see, there is redundancy in that every GPU is holding all of the parameters during the training. So what Zero proposes is that instead of saving the entire model, let's shard the model across GPUs. So now GPU 0 will hold the first shard of the model. So we're going to shard the optimizer states, the gradients, and the parameters. and each GPU is now responsible for a different shard. But now during the forward pass, all the models on the different GPUs will need this shard, right? All of the GPUs will need this shard to progress the forward pass. So that's why the GPU 0 will communicate its shard of the parameters to all of the other GPUs to perform the forward pass. Now, once the forward pass is completed for that shard, we're going to erase it. We're going to remove it from all of the GPUs and move on to the next shard, which is held by GPU 1. GPU 1 will send its shard to all of the other GPUs so we can do the forward pass. And so on. We're going to remove all of the model parameters except from GPU 1, which is responsible for this shard. Now GPU 2 is going to communicate its parameters to the rest of the GPUs. Let me fast forward. So once we reach the end of the forward pass, we're going to calculate the loss. And keep in mind that each GPU is seeing now different part of the data. So the loss will be different on each GPU, which means we need to synchronize the gradients. So during the backward pass, we're going to generate local gradients on each GPU. But now all of the GPUs will communicate their local gradients to GPU 3, which is responsible for this shard of the gradients. And once we're done, both the parameters and the gradients will be removed from all the GPUs except for GPU 3. Now, to progress the forward pass, we still need the parameters. So GPU 2, which is responsible for this chart now, communicated to the rest of the GPUs. We progress with the backward pass. Communication happens. And then this is repeated 2 more times for GPU 1 and GPU 2. So let me fast forward. How is this different than FSDP? Nick is asking. This is exactly FSDP, but it was introduced by DeepSpeed first as the stage 3 optimizer, and later adopted by PyTorch as FSDP. Okay, so now once we reach the end of the backward pass, now we need to perform the model weight update. So we take the optimizer states and we update them based on the gradients. And finally, we update the parameters based on the gradients. But now these parameters are saved in FP32. We want to perform the computation in FP16. So that's why we downcast. So we take this FP32 copy and we downcast it to FP16 with each GPU copying only the shard that it's responsible for. So this is the process. This is the forward pass and the backward. This is just one iteration of training with the 0 stage 3 or FSDP. Now, what is the advantage of this? We looked at these 3 blocks, right? The blue, orange, and green. We also have one more block, which is the activations. This was sitting on the top. Basically, as the forward pass was progressing, we're saving all of the activations. So the total memory that we need to save is the memory of the model parameters, the memory of the optimizer states, and the memory of the gradients, in addition to the activations. So these are the intermediate values that we get, the output that we get from layer to layer. Now, if we were to use the regular data parallelism, then we are limited by the memory of the single device. If we were to use 0, then we are limited by the aggregate memory of the entire system. So let's say we have 1,000 GPUs with 16 gigabytes of memory for each GPU. If you want to save a model in 16-bit precision, then we need around 16 terabytes of memory. So if we just divide the 16 terabyte by the number of GPUs, we get the GPU that is needed the memory that is needed per GPU. So this basically allows us to scale linearly, right? With the number of GPUs, we can reduce the memory linearly. Furthermore, there are more advanced solutions such as zero infinity, where we can offload some of the model parameters to the CPU memory or NVMe disk. So that gives us even more space to store things in, but this will impact the performance significantly, and that you have this constant data movement between the host memory and NVMe and the GPU, and the data movement can become a bottleneck very quickly. Now, is this all that we need? In the sense that, okay, like the more GPUs we introduce, the less memory that we need. We're scaling linearly. Is that all we need? Is that the final solution? The answer is that not exactly, because sometimes the one operation that we want to perform on the GPU, like the matrix multiplication operation itself, is too big to be performed on the GPU, so we need to split it across multiple GPUs. So that's why we need model parallelism or tensor parallelism. We can combine that with data parallelism and pipeline parallelism, and we get 3D parallelism. So zero is very good because it's easy to use, but it will not give us the best performance. So that's why we need tensor parallelism. This is just an LLM model that consists of many matrix multiplication operations. Matrix multiplication happens on the input tensor and the model weights. So the input tensor has the dimension of the batch and the hidden dimension. So the hidden dimension is just how we represent tokens or words within the model itself. And we multiply by the weight of the model to get the output and feed that output to the next layer. With tensor parallelism, we chunk the matrix multiplication operation across the GPUs. So GPU 0 will get these columns of the input tensor, and then these rows of the model weight tensor, and then it will give us an output that is of the original size. If we were to do this on a single GPU, and the GPU 1 will take the other half. But now we have these two outputs that are different, of the same size. All we need to do is perform a summation operation. So that's why we need an OR reduce between these two GPUs. So tensor parallelism is very communication heavy. So we try to keep all of the communication within the same node. And then across nodes, we perform parallelism schemes that are less communication intensive than tensor parallelism. So this is an example of 3D parallelism where we have tensor parallelism across 4 GPUs, and then we split the model itself into 4 pipeline stages using pipeline parallelism. And then this combination of tensor parallelism and pipeline parallelism can compose a single model replica, and this model replica can be copied, right, as a DP unit, as a data parallel training unit. But then once we know the model size and how much TP degree we need to use to fit that model and the GPU, how do we really place it and the network topology that we have? So what we do is that keep as many TP tensor parallel partitions as possible within the node. So again, TP is very communication heavy. Let's try and keep it within the one node. Now, if the model fits with TP, then that's great. We don't need to do anything else. Just replicate it with data parallelism. If it does not fit, then we start using pipeline parallelism. So pipeline parallelism uses point-to-point communication. It's not communication heavy. We can distribute things across nodes. That's fine until we are able to fit the model in the memory. And then until then, we won't replicate the model on the multiple DP ranks. So we only replicate with DP once we are able to fit the entire model. So before we move on, I see a question on this figure. I'm seeing data parallel, pipeline parallel, and model parallel. So model parallel is basically the tensor parallel. These are interchangeable. Model parallel is the larger umbrella, and then under it, tensor parallelism is what usually is used. Okay. So if there are no further questions, we can move to lab 2. So lab 2, we will train an out-of-core DNN model using deep speed. So we're going to use the zero optimizer, the first solution that we introduced, with the BERT 2.5 billion parameter model. We're going to try and train it on a single GPU and a multiple GPU. Let me open my terminal here. So again, just you need to cd to lab 2 and copy the command from the README file and execute it. And in here, we will see a lot of output. It's basically just the logging that is performed by both PyTorch and DeepSpeed. So it's loading the different libraries. And as you can see, the CUDA visible devices is just 0. So just one device is visible. Let me just open the README so that if people want to run this, they know which command to copy. So this is lab 2, just cd to lab 2. And then for the first experiment, you need to copy this and run it. So I have the output ready. Yep, this is the single node. And as many of you have already seen, we run into this CUDA out of memory issue. So Torch tried to allocate 16 megabytes, but then it reached the limit of the memory on the GPU, and that's why we're getting this out of memory problem. This is intentional, just to show that you cannot really train this model on the single GPU. You will need multiple GPUs to do it. So this is the now on the 2 GPUs, so exactly the same model with the same parameters, but the difference is that we're training it on a 2 GPUs. And after all of this logging, we should reach point. Okay. So here we're seeing output from rank 0, which is allocating memory, different shards of the model on different GPUs. And it's progressing, so global step 3 to global step 4 and so on. We are training for 10 iterations here. But as you can see, the script exits successfully, which means the training is complete for these 10 iterations. So there is a question on Slack. You said 0 supports CPU memory offload. Could that solve the memory issue? Yes, it does solve the memory issue. However, CPU offloading is very slow. So that means we're going to introduce an overhead. So yes, you can fit very large models now, but then the training will become very, very slow. The reason is the constant data movement. Even if we try and pipeline it, hide this data movement, the overhead is just too much. It will affect the training significantly. Can you go back to the initial running of the program? Could you clarify, Alex? Like here, the initial
Initial.
here? Is there a specific part you'd like me to explain? I mean, this is just calling DeepSpeed, the DeepSpeed library with this host file. It will have the two GPUs, two GPU nodes in it. And then we're running this training per BERT, the BERT model with DeepSpeed script. We're checkpointing the model. So we're saving so often we're going to save all of the model parameters. And then these are just model specific parameters. So how many layers in the model, the hidden dimension, and the batch size. The batch size is just one. So this is the smallest that we can choose just to be able to fit it on the two GPUs. And we're training for 10 iterations.
Yeah, so there is a question I can answer.
Sure.
What is the difference between scale up and scale out? So again, we'll discuss that in the afternoon tutorial in much more details. So the broad idea is the scale up. What is happening is that within the node, like how many CPU sockets you can have, how many GPUs you can have, and very latest you can have up to 8 or 16 GPUs, depending on, again, PCI Express specifications and all. So that means scale up. We are trying to make that node fat and fat. But as we saw, I mean, some of this training requires millions of GPU. You cannot have a single node with millions of GPU being connected. So this is where we have to use multiple of such nodes, and that means scale out. So please join the afternoon tutorial. We'll go into more details on the interconnect protocols, issues in both scale up and scale out. Any other questions, comments before we go to inference? Okay, so might be Nawras, please proceed. Yeah.
All right. So yeah, I mean, if you have any issues with running these labs, let me know. Also, like I'm just showing you the final script to run everything, but like underneath there is a Python script with many lines of code. You can just access it right from your tutorial account. Take a look at what's happening. If you have any questions, I'd be happy to answer it on Slack, even if after the tutorial itself. Okay, so everything that we've talked about with data parallelism, with advanced distributed training, zero and 3D parallelism, this is strictly for training, but some of these solutions can also be applied to inference. So what is the major difference between training and inference? With training, what we're doing is model learning. What is sensitive, or what we care about, the objective is the throughput. So we want to process as many data samples in a given time. And with inference, it is user facing, so there is no learning happening. And the sensitivity is more on the latency part. So we want to be able to generate the text within the human reading speed. So latency is usually like below 0.05 seconds per token, per word. That's the latency that we aim for. With training, we do the forward pass and the backward pass because we need the backward pass to update the model weights. With inference, we only need the forward pass. Usually the forward pass is just 1/3 of the computation. So you can expect inference to be 1/3 the computation of training. So usually with inference, we have smaller batch sizes, but we have many, many user requests that arrive randomly at different times. We don't need model weight updates. So even the optimizer states, these we do not need to save. This the huge green block that we saw in the zero optimizer animation. But still, like the model parameters can be too big to fit in the memory of a single GPU, so we might still need tensor parallelism or pipeline parallelism. Um, and what is most important is the response time. As I mentioned, it should be faster than the human reading speed. Now, there are different inference scenarios. We might have online versus batch inference. With online inference, it's real time, and latency is what we focus on. This is like with if you're using a chatbot like ChatGPT, latency is the most important factor. But with we have also the batched inference, in which we care about the throughput. And both of these things can be important, right? The batching if you have many users and latency for the single user. Um, but inference itself can happen on different systems. So it could be on the edge or the HPC system or cloud system. Usually on the edge, we care about latency. So let's say we have a camera or a drone that needs to take images and then make decisions. Latency is what's important. With the cloud inference or HPC inference, throughput is what we care more about. These are the large servers that host these huge models where we need to um, basically respond to requests that come from many, many users at the same time. Now, one other thing to consider is making the model smaller. So we can quantize the model after training. Um, so let's say the training happens in FP32 or FP16. Can we quantize it to FP8 or even lower than that, maybe int 8 and int 4, without really sacrificing the accuracy? So this is one of our earlier work where we looked at different models, like the DenseNet, VGG, and we looked at different quantization strategies. So some of the quantization can happen during the training, meaning we are doing training-aware quantization. So even training happens in the full precision and like either FP32 or FP16. We need to calculate some um, uh, basically counters or parameters that will allow us to perform quantization more accurately later on. But you also have static quantization. This happens entirely after the model training. And as we can see with different models, we're going to get different latency when we do the quantization, latency benefits, and also the accuracy will be affected in different ways. Now, we talked about batching. When we have multiple requests that are coming that need to be processed by the system, let's say we're doing like LLM inferencing, we have request 0 that comes at this time stamp, request 1 comes at this time stamp, and so on. With dynamic batching, we wait for a certain amount of time, let's say half a second. We collect all of the requests that we can collect before this timestamp and batch them together and do the processing in parallel. Now, the problem with this approach is that you have this segment of time that you need to wait for until you process the request, right? So what if request 3 comes at this timestamp, 510 milliseconds? That means we need to wait until the 1 second timestamp to be able to start processing this request. So it's going to take a long time. Concurrent instances mean we're going to have multiple model instances. So we have all of the weights of the model available on like either a single GPU or multiple GPUs. The problem with that is the redundancy. So we have the model occupying memory and the GPU, and as we saw, those larger models will take a lot of memory, so this will degrade the performance. What we proposed a couple of years ago is a method called temporal fusion. It's also known as continuous batching, which is now the state of the art. where you have a main inference stream. And since inference happens in iteration, that is, you feed the model the input, right? The question, the query, and then it generates one output token, and then takes that one output token and feeds it as input again. So since we have this step that keeps iterating, can we insert the requests in between these steps? And this is exactly what this solution proposes, and it will keep the balance between the latency and the throughput. So it will achieve both the best latency and best throughput. And if you're interested in learning more about this solution, you can just search for this paper. One more thing to keep in mind when we use continuous matching is that we need to reorder the buffers, the temporary buffers on the GPU itself. So as requests come and finish, we need to keep in mind that we'll have these gaps within the memory. So as new requests come in, we need to reorder the memory so that we have all of the computation happening in a relatively continuous memory block. Okay, I think, do we have any questions?
Any questions on the inference part? There is a question, can the same physical GPU be used for both inference and training at the same time?
Okay. So, I mean, usually we do training and inference separately because they are done for different purposes. So first you train the model and then you deploy it for inference later on. Is it possible to run both workloads at the same time? Yes. So let's say you have it like a system with many GPUs, but then you have many users. Can you basically divide the GPU itself so it's that it accepts both workloads at the same time? That is possible, but it's not very common.
There is another question from Bob. How is the per session/user continuously growing context maintained if you only have a single inference instance?
Yeah, that's a great question. So what we basically do is when we batch the requests, right? So if you have multiple requests and these are batch, all of them will be processed at the same time. So that's how we maintain the inference. Now, the second part of your question, the context is continually growing. That means the computation is now more complicated, right? That's why we need what is called KV caching. So instead of repeating the same computation over and over, we cache some of the intermediate results that we got earlier, and then we reuse this cache. So this is like a memory computation trade-off. But it's very efficient. Now, this will like support context length up to 8K, 16K, but then beyond that, we need more creative solutions. So maybe we'll offload some of the KV cache to the CPU, or we need to compress the KV cache, try and maintain the accuracy when we compress it. So yeah, this is an active area of research. But yeah, it's like main solution is KV caching, basically. Okay, next question. How would data parallel, pipeline parallel, and model parallel work in systems where different types of processors are being used to process different kind of tensors? So yeah, I mean, this is where workload balancing is needed. When let's talk about data parallel training, we will give let's say we have an A100 GPU and a V100 GPU. We know that A100 can process more things, so we'll give it more data samples, and the V100 will give it less data samples. So that's with inference. It's like we don't need to do any communication, right, if we're doing data parallelism. But then if it's training, we have a weight, right? For each device, we have a different weight because this GPU is only seeing a small part of the data. This GPU is seeing a large part of the data. So when we do the model update, each GPU will have a different weight on how much we update the model itself. Dr. Panda, how are you doing on
Yeah,
time?
let's
I can
address one or
answer
two.
these in
Yeah,
chat.
go ahead shortly. We have to finish up in 12
Yeah.
minutes,
Yeah,
but let's answer some of the questions. Okay.
sure. Let me
Uh,
respond in Slack channel.
no, go ahead if you want to, or you want to do
Yeah, I'm
offline.
thinking I'll
Okay,
answer in the
okay.
Slack channel while
Yeah, so that we can finish it on
Mhm.
time. Yeah. Okay, so let me share then. Just to give me a minute. Um, okay, can you see my screen?
Yes.
Okay. So I think we are almost at the end of the tutorial. I would like to indicate again some open issues. I think a lot of questions are coming. I mean, these are all, as you know, this field is very vibrant. But here I'll just give a very high level some of the open issues and challenges, and then try to conclude the tutorial, and we can have offline discussion on the Slack. So here some of the very high level things I want to say, like the convergence of machine learning, deep learning, and HPC. One angle, then the what kind of like a benchmarks and thoughts on standardization effort, because a lot of solutions are coming together. And we talked about like a billion parameters and all, but gradually the field is moving to trillion parameters models for training and inference. And then of course we touched a little bit like a energy aware, fault tolerant, so that is also becoming very important. And just in the last section, we covered this latency, high throughput inference for a range of device. So let me go into a little bit more in detail. Like if you're a student or a researcher, these are some of the topics you can actually focus on your thesis. So convergence of the machine learning, deep learning, HPC is always like a these questions started like almost 10 years back, but now I think people are realizing that they are all together. Like is machine learning, deep learning, and data science is an HPC problem. Distributed model training is definitely an HPC problem. We saw because people want to do it in a like a 1 million GPUs and all. Inference is gradually hitting there. Again, it's based on like as the newer models are coming, just like ChatGPT. All the different vendors are providing this. Uh, the Gen I interface and all. So gradually it is trying to become an HPC problem. Okay. And and then the why HPC can help, we saw like the decades of research, whatever has happened on the communication models, performance optimizations, they are gradually being built into all these upper level software stack. And some of the needs for the MLDL frameworks are exact match because they're also very compute intensive as well as like a communication intensive. And we saw some of these needs like a large message communication, CUDA aware communication. So even though like some of these concepts started like in the HPC, gradually people are seeing the big benefits in the AI work also. Now, as the different hardware softwares are coming, there has been a lot of discussions like how to provide like a standardized interface. One way you can think of it, some layer convergence is taking place like PyTorch. At PyTorch, then people are coming, but might be again some people are still in the TensorFlow. People may come up with some or other model. And especially to benchmark, again over the last decade, there a lot of work happened for different benchmarks, and I think the ML PORF is getting more traction. So if you go to the ML4, they have very specific way. How do you measure? Just like some of you are familiar with HPC, like a LinPack or HPCG or like a Green 500 list, top 500 list. So a lot of those things have been standardized. So gradually in the AI world, similar kind of things are happening. I talked about the trillion parameter. In fact, if you go to this link, there is a trillion parameter consortium which was initiated, I think, two years back by Argonne National Lab, and it is gaining a lot of momentum. A few weeks back, actually, they had their event, hands-on event in San Jose. I think almost 400 people from many countries attended. So please take a look at that program and then see how that field is evolving. And that also includes, I mean, here we went only remained in the lower level, like a training and inference basic principles. But now the agentic computing is coming, the AI for science. So all those things are built on top of these, the inference and training. So that is the field I think which will be across all disciplines will expand. So this is where, if we project kind of things for the next 10 years, you will see these kind of extremely large scale data centers. Out to 1 million GPUs will be coming. And then this is the different paradigm, like the accelerator and memory subsystems. Can it actually hold that model? And then this is where I think there are some questions like a CPU offload memory. There are technologies like CXL. Even if you think of like a Ultra Ethernet consortium, UA Link, everybody is heading in the very similar direction. Okay, like what can help to keep this model in the memory, large model in the memory, and have CPU or GPU or even a hybrid way to execute on top of that. So that's where you will see the next generation architectures and algorithms are coming or being proposed. And the two other big things which we didn't touch here because we had a limited time, but it's very important, is this training models with billion parameter requires extremely large data center. They use like months of training time, you would have heard, and it consumes significant energy. And this is where, like, even big data centers, people have even started talking about using atomic energy. Okay, like the regular data centers, regular power cannot be there. um, and the more important thing, there has been a lot of studies in the recent years, like these GPUs, because irrespective of like the vendors, they go through failures. And then of course you have a software stack, and these are all based on like a lot of time open source software. So it goes through a lot of failures. So once you, let's say you are doing the training, there's some failures happen. I think Nawras indicated like a PyTorch has some checkpointing, but then especially for very large systems, the checkpointing itself is consuming a lot of time. Okay, so all those work, what happened in the HPC field, um, 10 years back, 20 years back on high performance checkpointing, those are again coming back into the AI world. So there will be a lot of significant focus on the next generation of hardware and software for reducing energy consumption, and also newer checkpointing and fault tolerant schemes. So then I think in the last section, we are touching some of the questions came like that. Like if you see inference, I mean, the training is, of course, big companies are trying to do, let's say OpenAI, Facebook, Microsoft, but fine tuning and inference, those are very much spread it across. Okay. And especially if you see inference, you need to have solutions for all different disciplines. Okay. Like it might be engineering, medicine, agriculture, even the principle is the same, but the data sets, the model size, the vocabulary, and everything is different. Okay, even though you would take just an LLM and all. And then you have a lot of range of edge devices. It could be laptops, smartphones, drones, dedicated devices. So this requires some generic solutions, some very customized solution. Okay, and this is where a lot of actions are happening, and that means that we require inference schemes with low latency. Of course, like from an individual perspective, if you are doing a ChatGPT query, you want your response to be very fast. But if you see on the server side, millions of such requests are coming. Okay, so you need to provide the high throughput. And then is a combination, you also need to reduce the cost. You might have heard like a lot of these business models are coming up. Every query you do, like a ChatGPT query, it costs you some X cents and some amount of like a watts per power. So you are trying to reduce that kind of a cost and the power requirement. So this is where also a lot of actions are happening. There's a lot of co-designs are happening between not only computer scientists but also with the domain scientists, and so that this inference workflow pipelining involving the edge devices, network, and backend servers need to be very heavily optimized. Okay, and based on the need. So these are again some of the things I just outlined here. This is not exhaustive. This field is very vibrant, and a lot of work is taking place here. So with this, let me conclude here. As we saw, like there is exponential growth is happening in machine learning, deep learning, data science, and here we provided kind of an overview of issues, challenges, and opportunities, saying going over the entire stack, and then how do we design these communication runtimes. And we also went over some of the basic principles and practices. We worked on a set of hands-on exercises to demonstrate the complex interaction between what is happening in the DLML middleware with the underlying HPC technologies and middleware. So this requires collaborative effort to achieve full potential, and that's what you will see for the next 5 to 10 years. A lot of new results will be coming out. So with this, I'd like to thank all our sponsors. I mean, we are bringing based on all these our research, our research results. So these are the funding acknowledgement we'd like to give. But more importantly, these are all my heroes. So what we are bringing here is actually a work of 25 years. A lot of people have come, students, staff, and they are now placed in a very in all different companies, national labs, industry, academia. But we are able to continue these projects and then bring the solutions or the knowledge to all of you. So I'll officially conclude here. This is a half-day version. I also want to indicate that we have a full-day version of this tutorial accepted for supercomputing. If you or any of your colleagues would like to attend that, so there we have much more expanded materials in all the sections, including the hands-on. So we'll go over it. Today morning also we got a notification this tutorial has been accepted in HPC Asia 2026. That is the combined HPC Asia and SC Asia. We'll be offering that in the end of January. So like this, we offer this tutorial at many other places. Depending on where you are in the world, you are welcome, and your colleagues are welcome to attend this. And then a lot of these questions came about the high performance interconnect and all. So that will be our afternoon tutorial. There is a lunch break for 1 hour, and then we'll be starting on that, which will go much more deeper into the interconnects, the protocols, the switches, all the scale up, scale out, all those issues we'll be talking with respect to a lot of different technologies. So I think we are exactly on dot. If there are any other questions, please feel free to post that into the Slack, and we'll be very happy to answer it. So on behalf of both Nawras and myself, I'd like to thank all of you for attending this. Any other final questions or comments before we close it?